Morning, good afternoon, and good evening, everyone. Welcome to the SCS Annual Conference. We're delighted to have you join us. My name is Nadia Assad, and I'll be your host for today. So you'll see me pop up on your screen from time to time to just let you know where we are in the program. So let's get right to it. First off, Professor Green and Professor Corey, the two co-directors of the Energy Futures Lab, will start us off with the opening remarks. Thank you. Over to you.
Well, thank you, Nadia. Good afternoon, everyone. Well, and good morning or good evening, depending on what time zone you're in. A pleasure to be here today to see the culmination of the year of study of the Sustainable Energy Futures MSc students. So welcome first to our cohort of students. Welcome to the supervisors of those students and the friends and families and supporters. So you're very welcome, and I hope you have, and I'm sure you'll have, a very interesting and engaging day today and a second session tomorrow. This is always a great event. It's a culmination of a year of very hard work by our students. We put in front of our students a wide range of challenging material in the talk courses, and then unleash them on some very difficult and interesting problems in the energy domain for the projects. And today we get to see the fruits of all of that, and particularly the outcomes of the projects. And it's astonishing the range of activities that are covered and the insights that the students generate from the work that they do. It is really a great class to teach. I've enjoyed teaching the class. It's a little while ago now. I was teaching back in November and December, but it's always great to engage with such an enthusiastic, knowledgeable and curious group of people. So congratulations on reaching this stage, the very close of the course. I hope you, as the students participating and presenting, enjoy the occasion. You should do. It's a chance to show your work, and I hope everyone listening enjoys too. And now I'll hand over to Anna and hope that I left her a few things to say as well.
Thank you, Tim. Thank you very much. And a warm welcome, a very warm welcome from me too. It is always a pleasure to be able to interact with you, and I'm sure that you have been challenged in very many different ways throughout the year, also considering the COVID circumstances we all had to face. So you should be especially proud that you have been able to complete the work. I hope that you have had a bit of time to reflect and enjoy how much you have achieved during the summer. And please support your colleagues during the presentations today and tomorrow, encourage them, and do remember to stay in touch as we move forward to the next step in the process until your final graduation. So I wish you all the very best, and back to Nadia to take us to the next part of the session.
Thank you very much. So we'll move straight to the first session for today, which is on low carbon living and transportation. Yeah, straight to the presentation.
Hello, everyone, and thank you for joining us. My name is Ilya, and I'll be introducing our presentation on low carbon living and transport. The domestic sector, which encompasses our living and transport habits, is important to consider when meeting climate goals. Personal transport and building energy demand are the highest emitters in the UK, accounting for 16% and 23% of total annual greenhouse gas emissions, respectively. Decarbonization of domestic energy consumption has clear benefits for the environment, but also positively impacts electricity and heating networks with proper forethought and resource management. Our goals for this presentation are to provide you with insights regarding cutting-edge research on the decarbonization of domestic consumption, and present potential solutions for domestic decarbonization through an analysis of relevant technologies and use cases. We will begin with an exploration of the technologies which can reduce the emissions of buildings. First, Maggie will present her work on supermarket retrofits to reduce the emissions of commercial buildings. Then, Mira will discuss the potential for a combined Rankine cycle and heat pump system to meet domestic heating demand. Despo will follow with a techno-economic and environmental analysis of battery storage as a method to increase domestic electricity demand flexibility. Havoc will then transition to electric transport, discussing the economic benefits of introducing e-roaming into the UK EV landscape. Afterwards, I will present a unique EV case study to highlight the importance of local considerations on understanding EV impacts and charging network utilization. Finally, Christopher will conclude the presentation by presenting his work on modeling residential energy use with limited data availability. I will now pass it on to Maggie to start.
Thank you for that introduction, Ilya. I'm Maggie, and my thesis focused on an assessment of supermarket retrofits through dynamic simulation modeling, which was conducted in collaboration with an industrial partner who have aimed to reach the net zero target by 2040. It's evident that reaching the net zero target will require the built environment to decarbonize. In the UK, buildings account for a significant portion of total greenhouse gas emissions and energy consumption each year, with supermarkets alone emitting 4 megatons of carbon dioxide. Considering that 80% of the existing building stock will still be in place in 2050, the solution is likely to be enhancing the performance of these buildings through retrofits. Energy demand can be reduced through passive strategies, whereas energy efficiency can be increased through active strategies. So the aim of this project was then to assess the impact that both passive and active strategies can have in reducing the energy and carbon intensity in existing food retail buildings. The method employed for the research entailed a case study analysis of 8 supermarkets in central London, which allowed for a building archetype to be created based on their shared characteristics and parameters mentioned in this slide. This can be a really helpful method to assess retrofit strategies that can be applied at a greater scale. This archetype was used to model a base case building in a dynamic simulation tool called IS, which is a software capable of absorbing information and producing outputs of the dynamic behavior of a building in half-hourly intervals, as seen on the graph on the right here, which is a power demand graph where the pink and green represent gas and electricity respectively. So 2 retrofit scenarios were designed in IS. The first scenario focused on passive strategies, which included an external wall render to reduce the level of thermal transmittance and hence reduce the heating demand, a lobby to minimize uncontrolled air infiltration, and a green wall by the front facade to provide for passive cooling. The second scenario focused on an active strategy to electrify the primary heating system by replacing existing gas-fired boilers with an air source heat pump. The main findings from the study revealed that both the passive and active scenarios were able to achieve a lowered energy demand and carbon intensity, which is a measure relating energy in kilowatt hours to per square meter of floor area inside the supermarket. The active strategies was, however, more effective in reducing total energy demand of 18% compared to 2% from the passive scenario, despite the electrical energy use intensity increasing by 16%. The switching from gas-fired boilers to an air source heat pump also gave a 15% reduction in emissions, which resulted in a carbon abatement of 57 tons of carbon dioxide equivalent for 1 year in operation, which is a significant figure considering the whole lifetime of a building. So what was learned from this process? Decarbonizing the building stock starts with careful monitoring of energy performance. This is why a case study of 8 supermarkets was performed. Only when the greenhouse gas emissions and energy demand attributed to a building's operational phase are fully understood can one really grasp the contributions energy-saving measures can make to climate mitigation. It was found that utilizing a modeling tool to assess a variety of strategies is a viable approach to evaluate the impacts these can bring in both a time and cost-effective way. But however, the upscale of retrofits for energy efficiency is dependent on a trajectory set by policymakers, which should be based on a clear framework and incentives for attaining the net zero standard. This is something that is currently lacking. And informing the energy and carbon mitigation potential these strategies have will provide beneficial for commercial businesses on their way towards net zero. It was seen that the heat pump in particular offered substantial energy savings and carbon abatement potential. Indeed, this technology will play a central role in decarbonizing heating, a topic that Mira has researched in greater depth.
Thank you, Maggie. My name is Mira, and my thesis investigates the performances of a novel combined organic Rankine cycle and heat pump system, which is designed for domestic heating and could potentially be a solution to decarbonize the heating sector. At present, heat accounts for around 50% of total energy consumption and around 30% of the total carbon emissions, of which around 80% have been utilized in domestic sector or buildings. Therefore, it's urgent to decarbonize the heating sector. Several domestic heating technologies are available in the market now. However, they all have some drawbacks as shown in this table. Therefore, novel combined organic Rankine cycle and heat pump system is proposed, which aims at using cheap gas as the heat source will be more efficient than the techniques such as boilers. The schematic of this combined system is shown in this slide, along with its working principles. One of the main innovations of this system is that power consumed by the heat pump compressor is directly supplied by the organic Rankine cycle. Cold sources such as water can be heated via condensers of both subsystems, and the order of it being heated also affects the system performances, which will be discussed later. To assess the system, several analyses were conducted, including comparisons of the system's configuration, thermal economic evaluations when different working fluids are applied under varying boundary conditions, and case studies of when the system is used differently. Two main indicators are used to evaluate the system, namely its heat-to-fuel ratio and specific investment cost. The performances of the system are simulated using the existing MATLAB models. So which design is better? As shown in the graph, when cold water flows through the heat pump condenser first, then the condenser of the organic Rankine cycle, the system demonstrates better performances from both thermodynamic and economic aspects. Since higher heat-to-fuel ratio and lower system-specific investment costs are achieved at the same time. Therefore, further analysis is carried out based on this design. And what about the system's thermal-economic performances? It can be seen that its heat-to-fuel ratio increases with rising ambient temperature and reduces when higher heat provision temperature is required. Additionally, its specific investment cost reduces with increasing ambient temperature and heat provision temperature. Although applying different working fluids does not largely affect the heat-to-fuel ratio of the system, R600 and R62 are regarded as the most promising working fluid combination, as it achieves the lowest system-specific investment cost. In practical application, the system can be used for space heating only, or for both space and water heating, of which the heat provision temperature is different. According to the results, it's reasonable to state that how the system is used depends on the actual situation. And system of larger heat capacity is preferred since it has lower specific investment costs. The key findings of this combined organic Rankine cycle and heat pump system are summarized in this slide. When appropriate working fluid are used, a 10 kilowatt system whose heat capacity can cover a normal household in the UK has the specific investment cost of lower than £500 per kilowatt. According to the research, this value can be competitive compared to some current heating technologies in the UK. It means that in the future, the system, especially of a large scale, could potentially be a cost-effective and efficient technology in heating sector. However, I should declare that most of the analysis conducted in my project was theoretical, so more research and evaluations are required before the system could be actually popularized. Next, Despo will introduce another technology that improves the energy efficiency and decarbonizes the residential sector.
Thank you, Mira. My name is Despo, and my project focuses on technologies and modeling approaches that can aid to the decarbonization of the residential sector, with particular interest in battery energy storage application. As a major source of energy consumption and greenhouse gases, buildings have a crucial role in the transition towards a lower carbon and sustainable society. The rapid growth of PV installations in residential buildings increases the production of intermediate electricity and the need for storing excess power, necessitating the use of advanced technologies to provide sufficient flexibility cost-effectively. In our case, a residential lithium-ion battery, which is one of the most mature technologies for residential applications, was used with on-site solar PV generation. Technical and operational characteristics are taken into account, combined with intelligent control and operational strategies to assess the economic viability of the system and the potential for environmental benefits. The following results obtained using a MATLAB-based framework. Battery storage can be used to provide services such as the management of the intermediate generation and the balance between supply and demand, considering that in residential buildings, the high generation from PV and the electricity consumption profiles usually do not match, leading to a waste of produced electricity, and the shift of demand in off-peak hours where lower electricity prices occur. So with integration of storage, the user can benefit financially with the reduction of electricity bill, increase the PV self-consumption, reduce emissions, and relieve the grid. However, since batteries are made of chemicals, the way the conditions under which they used have an impact on their lifetime, with battery operation called loss in capacity and power capability, which will lead to a point when battery will need to be replaced. To address this issue, degradation cost is calculated as a function of the capital cost and the capacity fate. To avoid quick degradation, the control of battery charging and discharging process is achieved with the primary target to meet as much as possible of the electricity in demand during peak hours with the least potential influence on battery's life, considering that maintaining the state of charge levels high can accelerate degradation. Also, as battery storage applications grow, there have been increasing concerns about the carbon emissions associated with their production. For that reason, to evaluate the overall environmental performance of the system, embodied carbon footprint is calculated as a function of the usable energy delivered. The decision of battery size is of great importance when evaluating the economic performance of the system, including the effect of degradation, with the results of the performance sensitivity analysis indicated that has significant impact on the total cost savings. On one hand, increased battery capacity can prolong battery life as it can deliver the same amount of energy in lower state of charge levels, whereas a small one will degrade faster but with a lower cost of replacement. As for the environmental impact of the system, after it was observed that the system does not provide satisfactory carbon savings when the battery embodied carbon footprint is considered, a key point that arises is whether it will still worth to use residential batteries as we shift to the decarbonization of the grid. Due to the complexity of assessing the future overall carbon intensity, considering that the grid should be assessed as a whole, including, for instance, the potential use of large-scale battery storage and their impact, there is still debate in terms of sustainability. So from the results, it is concluded that the use of residential battery storage is proven to be economically favorable, with the correct battery sizing and operational management maximizing the profits. However, in general, it is recommended using more realistic prediction profiles when it comes to the proper management of the system. Unfortunately, the same cannot be said for the carbon footprint of the system, with environmental sustainable recycling technologies and the use of repurposed EVs batteries being potential solutions. Should be noted here that in that case, the aging of the battery should be tested before being reused, and its future degradation should be estimated. Finally, due to the significant advancements that have been observed through the years, battery energy storage must be compared carefully with alternatives in terms of sustainability, and also consider the integration of electric vehicles to provide further flexibility to the system. Further analysis for EVs will follow by Avik.
So thank you, Despo. As I'm Avik, and prior to joining the 2021 SCF cohort, I'd followed a career in international mobile telephony. Today, I'll present my research project, which aims to quantify the benefits of introducing roaming, which is a key mobile telephony capability to the wider public electric vehicle charging sector in the UK. With passenger vehicles and light-duty vehicles contributing 16% to the UK's greenhouse gas emissions, there is a UK-wide imperative to cease the sale of internal combustion vehicles by 2030 and hybrids by 2035, and to further accelerate the uptake of electric vehicles. 25% of car-owning households do not have access to off-street parking, and with this figure set to rise, there is an urgency to ensure that public charging facilities are expanded to meet the needs of these consumers if we're to meet the 2030 and 2035 deadlines. The uncoordinated and heterogeneous rollout of public charging infrastructure across the UK is creating a national imbalance in infrastructure deployment, with an oversupply in areas such as London and the South East, with a deficiency in the North East and North West of England, for example. Only 15 operators account for 75% of the nation's public charging infrastructure, which is contributing to consumer frustration with higher prices for charging energy and having to maintain multiple subscriptions. By introducing the concept of roaming, where an EV driver can plug their car into any public charging point and is billed centrally by their home mobility service provider, or even their domestic energy supplier, some of these issues and barriers could be lifted. Much like with mobile telephony, wherever you are in the world, you can turn your phone on, make a call, and you're billed by your home service provider. You may not like the size of your bill, but it just works. So extending roaming to public charging will allow operators to extend the coverage of charging facilities available to their customers without extensive capital investment and operational cost. This will help to facilitate better coordination on infrastructure rollout and coverage optimization, with the resultant cost avoidance benefits enabling higher revenues for the system operators and lower tariffs for the consumers. Multiple subscriptions could then be replaced by a single contract with the home service provider. And lastly, easing access to public charging facilities will hopefully alleviate range anxiety fears of potential EV owners and hopefully help to accelerate the transitions to EVs. So the aim of this project is to quantify these benefits in the form of what we call value pools. The model derives the value pools based on the annual growth of public charging points between 2021 and 2040 and was built around two key scenarios. Scenario 1 takes a more qualitative approach to public charging point growth and then follows a strategy blended from future end gain hypotheses and opinions published in the UK government briefing papers and further from publicly available consultancy reports. Scenario 2 takes a more analytical approach and calculates public charge point growth as a function of annual public charging energy demand from the expanding UK's fleet. Again, the input data was sourced from validated future scenario datasets such as the national grid. Each scenario then provided outputs for two pathways, one where e-roaming is adopted early in the transition to EVs and the other assuming roaming is not implemented at all. From the public charge point growth and energy demand outputs, it was possible to calculate and compare the availability, cost avoidance, revenue, and pricing value pool metrics. The value pools calculated from each scenario and pathway were compared and gave some very interesting insights. Firstly, the number of public charging points required by 2040 could be reduced by almost 1.3 million to 200,000 in order to meet the forecasted demand. This would help to drive a possible cost avoidance of £11 billion between now and 2040, with a further incremental revenue potential of up to £19 billion over the same period. So with the lowering of overall costs and the rollout and the optimization of rollout, we could see the floor price of charging electricity falling to as low as 8 pence per kilowatt hour by 2040. So in conclusion, the results of the research and modelling build a compelling case for early introduction of EV into the UK, as is the case in advanced EV adopted countries such as Norway and the Netherlands. However, to realise these benefits, policy intervention is needed to mandate e-roaming as a key component of the UK's electrification infrastructure plan, together with the adoption of a single standards framework to enable full interoperability between service providers. And finally, regulation on tariffs is needed to ensure consumer pricing remains at acceptable levels. So this research, whilst providing compelling insights, could be expanded to provide a more finely tuned set of results by introducing simulations of expected market consolidation over the next 20 years. And furthermore, we could introduce a dynamic spatiotemporal modelling of user charging behaviours. Ilya will now continue by exploring local idiosyncrasies in a real-world case studies of EV fast charging expansion in Alaska.
Thank you, Avik. I will now present my project, which attempted to understand the barriers to and impacts of electric mobility on a unique EV system, with a specific focus on fast charging infrastructure expansion. This was done through the lens of a case study of the municipality of Anchorage in the state of Alaska. The municipality of Anchorage is an interesting case study because of the unique characteristics of the environment and its residents. First, the cold winters make EVs more difficult to operate because of higher energy consumption. Second, residents have singular recreational opportunities as a result of the natural beauty that surrounds them. Finally, the state of Alaska has a uniquely low population density spanning a massive land area, which makes travel distances significant. The study is relevant because of increased interest in EVs in recent years, with federal funding currently being used to erect new charging stations and a utility proposal to reduce the demand charge. A systemic approach was taken to understand the issue of electric mobility and fast charging infrastructure expansion. Stakeholder interviews were conducted to learn of the current barriers which exist on this issue and what actions are being taken. This was supplemented by a survey of drivers, which aimed to understand end user motivations, travel behaviors, and charging preferences to educate future policy. Finally, insights from the two aforementioned methods, along with local demographic and environmental data, was used to develop an agent-based model in the program NetLogo, which examined EV impacts on the grid and the ability of existing infrastructure to meet travel demands. From this data, 2021 scenarios were run to understand the baseline load and utilization for weekday and weekend travel behaviors in the summer and winter. Then, interventions were included to see the impacts on feasibility of travel. 2025 scenarios were then run to visualize the grid impacts of increased EV penetration, and the effectiveness of workplace charging to reduce peak load was determined, both in the summer and the winter. The 2021 baseline scenarios indicated that weekday travel schedules did not require much utilization of the public charging network, with 86% of charging occurring at home. The more interesting results came in the weekend simulation, especially in the winter. For the weekend, agents were very likely to drive to a hiking location, which were usually located at greater distances than destinations in the weekday. The limited infrastructure in the most popular hiking region in the south caused significant queuing to occur at charging stations, as shown in the figure, with about 10% of the agents unable to make it home by the end of the simulation. It's thus highly unlikely that such recreational trips are made by EVs with the current state of the infrastructure. Interventions which improve the charging network were employed and run for a weekend winter specifically, as it was the most strenuous condition for the charging network and the residents. The addition of a single fast charging station with 2 level 3 ports, as well as an additional level 2 port at the most congested baseline station, were able to significantly reduce queues, with all agents able to charge before 10 p.m. and nobody getting stranded. The addition of the new station on its own did improve usability, but still resulted in a few vehicles queuing at the end of the simulation. This implies that simple improvements in the network can have significant impacts on mobility, although it is clear the solution must be multifaceted to produce a driving experience comparable to ICE vehicles. Finally, the addition of workplace charging was assessed in 2025 to determine impacts on peak load. Such an investment showed significant improvements in the summer, with a 35% reduction in peak load and 29% reduction in peak energy consumption, with a 25% workplace charging penetration. However, in the winter, the implications are not as momentous. While a 5% penetration does produce a 12% reduction in peak load and 18% reduction in peak consumption, additional availability through 25% sees minimal improvement. From the results of the study, it is clear that the current charging network does not support local recreational travel. However, simple improvements to the system can make this much more feasible. Secondly, local environmental conditions, such as the increased energy consumption in the winter, are important to consider as they impact the EV load and utilization of the charging network. This is especially true for future EV penetrations. While the simple addition of workplace charging was enough to reduce peak load in the summer, its effect is limited in the winter. As a result, the network operator or utility must consider additional methods, which are likely costlier, to mitigate negative grid impacts of future EV loads. To summarize, a systemic understanding of local challenges and barriers, as well as an accurate representation of resident behavior, are key to producing impactful recommendations for local communities in the transition to electrified transport. I will now pass it on to Christopher to continue the discussion on individual energy consumption and its impacts.
Thank you, Ilya. So my work will further highlight the human dimension playing a part in energy use. Specifically, it explores modeling residential energy consumption using data-driven techniques to circumvent the limited observability of occupant behavior. The Flamstead social housing estate was used as a case study for my thesis. It has 9 houses as shown and supports 172 buildings. It's recently undergone a retrofit where the thermal insulation of its external building fabric and windows was improved. This creates value in being able to effectively assess the impact of the retrofit by comparing consumption pre and post retrofit. As with all buildings, energy consumption is driven by electrical appliances, lighting, space heating, and hot water demand. But this is where the complications come in. Especially in a residential context, differences in energy behavior can cause energy use to vary by as much as 100% between dwellings. Empirical data from the estate revealed that indoor temperature needs varied by as much as 6 degrees at noon on the same day. It illustrates a big difference in reliance on gas. So to improve accuracy, differences in occupant behavior need to be accounted for. This can be done by obtaining time use survey data from the occupants to profile the activity in their dwellings. However, there was very limited survey data from the estate, but there is survey data of the general UK population. The methodology used to bridge this data gap was using first-order Markov chains. It is a stochastic algorithm that describes a sequence of possible events, in this case household activities, where the probability of each event depends only on the state attained in the previous event. To illustrate an example, general UK statistics have shown that someone asleep at midnight has a 99.4% chance of remaining asleep and a 0.6% chance of being awake at 10 past. With this algorithm, activity statistics of the general UK population were imposed on the occupants of the Flamstead estate. By adapting a model left open sourced by Loughborough University, data was synthesized using the Markov chain technique for an occupancy model that details activity. The non-zero probability of light sharing and appliance sharing between occupants, as well as the seasonal and diurnal variability of the weather, which affects external temperatures and indoor illumination, are taken into account by the electricity demand model and the irradiance model. The building thermal model and the hot water cylinder model describe thermal flows throughout the dwelling. Together with the heating controls model and solar PV model, all of these models were combined and further refined with parameters specific to the Flamsteed estate to produce daily electricity and gas demands. So here are the conclusions that were made using these tools. Different scenarios could be modeled to generate useful insights which would inform decision-making at a council level. One of the key insights was that there was less variation in energy demand between dwellings in winter than in summer. This means that councils could expect to see smaller differences between, for example, a 1-occupant and a 5-occupant household in winter than in summer. Appliance sharing and passive heat gains from occupants was also observed. Another insight was that improvements to thermal insulation from the retrofit had varying impacts on consumers who use gas differently. Consumer profiles on the extreme opposite ends of gas reliance could see a savings difference of 30p for costs and 1 kg for CO2 for an average winter day. In this figure, we see the effects of the season's variation on gas and electricity demand. As expected, the UK's heavy reliance on gas boilers to meet their space heating needs corresponds to the large gas demand oscillations through summer. However, the key insight from this is inferred from the larger scattered gas consumption on a day-to-day scale. This reflects a higher day-to-day volatility in gas demand than with electricity demand. So decision makers willing to preemptively assess the benefits of retrofitting an estate should consider these factors before embarking on a large-scale project. Now, I imagine that must have been a whole lot to take in. So to close, I'm going to provide a summary of the takeaways of our different projects, ranging from a technological to an individual and finally to a policy level. With the domestic and transport sectors being the largest contributors to the UK greenhouse gas emissions, we have hopefully shown you that there is potential to significantly reduce these emissions through the retrofit of energy-saving technologies in existing buildings, using alternative heating technology, introducing personal energy storage, easing the transition to EVs, and individual behavioral analysis. Specifically, Maggie's work has shown that assessing the impact of retrofit strategies can be done by simulation modeling. This can provide valuable insight into where measures can be applied to decarbonize the existing building stock, which is a critical factor for commercial businesses aiming to achieve net zero. Mira's work has shown that a heat pump system could be powered by the organic Rankine cycle so that affordable natural gas can be used while the system maintains reasonable efficiency. Additionally, since it is fundamentally fueled by heat, a wide range of heat sources can be used to power it. Despo's work has shown that batteries are economically viable. With optimal battery sizing and intelligent operational management, the impact of degradation and the corresponding cost can be minimized. However, there are concerns when the environmental impacts, including manufacturing, are considered. Avik's work has shown that in order for the EV transition to be successful in the UK and to maximize cost efficiency, roaming needs to be implemented very early for a smooth transition. This will require policy intervention and industry support. Finally, the works of Ilya and I have both led to conclusions about energy behavior. There are certain technologies that may be ubiquitous solutions to decarbonizing the domestic sector, but designing impactful policies should involve more consideration for demographics that represent the individual. So, what does this all mean? Well, we clearly have demonstrated that there can be a whole lot done to tackle climate change from the domestic perspective. The next important step for all of us to think about is how to link our conclusions and simultaneously deploy strategies to quickly and effectively meet net zero carbon goals. Thank you for listening, and we will take any questions you have for us now.
Thank you for that informative presentation. So for the panel discussion, kindly use the chat function to post questions to the panel. I'll hand over now to the chair, Dr. Audrey de Nazelle. So take it from there.
Thank you very much, and thanks for inviting me to share this session. I greatly enjoyed it. Most of it is way beyond what it is that I can that I work on, or even that I can understand. So it's very fascinating for me to hear all this. So I'm a senior lecturer at the Center for Environmental Policy, and my research is very much around understanding how we can build cities to be healthier, with a lot of focus on active travel and getting people out of their cars. So as you can see, not exactly what this is about, but I certainly have a lot of interest in the built environment in general and making it more low carbon and healthy. So while we wait for questions, I see there are already some questions. Gavin, have you already highlighted the ones that were? Okay. I just wanted to have a quick round of everybody before we go into the questions that are posted, and I'll take a look at them right now. Just to ask you, if you can each very briefly tell us what trade-offs all of you have suggested some kind of control strategy, some approach, some policy, and some of them explicitly addressed any kind of trade-offs and others less so. Could you each one by one in order of appearance tell us what you think is the greatest trade-off that's associated with the solution that you suggest as a possibility? Go ahead, I'll let you go in the order that you appeared in.
Yes, that would be me first. I think the biggest trade-off for my project, as this was specifically to inform different strategies for an actual commercial industrial partner, that it helped in their decision-making process and where to place their efforts to update the performance of their existing building stock. I thought that was quite helpful in sort of placing that into real-life application. It was the biggest trade-off for my project.
Great, thanks. Mira? We can't hear you. Are you speaking?
Yep. Can you hear me now?
Yeah.
Yeah, I think the most trade-off that I made is more like when I'm doing the thermoeconomic analysis of the system, I need to do some assumptions, like maybe like ignoring the heat loss between the components, or even like assuming the certain efficiency of the technology. Yeah, I think that's the biggest trade-off that I made. Thank you.
Thanks. Espo?
Yeah, I would say similarly to Mira, because my study has a lot of projections and forecasts associated with the final results, as we wanted to see the whole lifespan of the battery application. So it was a bit challenging because a lot of changes arise through the years, even in terms of cost or the decarbonization of a grid, which it was the main challenge in my study, that it's a bit complicated to accurately forecast how the carbon intensity will actually affect the results of the whole system.
Great, thanks. Avik.
Yeah, so I think for mine, firstly, mine was the static model, so it would have benefited from being able to simulate dynamic charging behaviors of driving patterns using agent-based modeling. So that was something that could be enhanced on that. I had to trade off on that. But I think also from a sectoral point of view, I think we're all hoping that people will be moving away from personal passenger vehicles to public transport. And so whilst I looked at 4 scenarios from the national grid, the future energy scenario, and I picked one that was relatively conservative, but actually I think, you know, I could have used a more aggressive, you know, scenario which saw a much faster ramp down of personal transport in the years 2035 onwards, and I could have used that, you know, to really push the agenda forward and say, you know, to look at, you know, moving towards public transport.
Thank you, Ilya.
Yeah, kind of building off of Avik. So I did use an agent-based model to look at EVs and utilization of public charging infrastructure, but I did have to make a lot of assumptions regarding the travel behaviors of the residents themselves. You know, although the actual behaviors and destinations are representative, they were definitely significantly simplified for the case of time and the actual model runtime. So that was definitely a trade-off in my analysis. Great,
thank you. And Chris, finally?
Yeah, really similar to, I mean, coming off of Ilya, it was the same with a lot of assumptions had to be made. But I think the main trade-off with the work I did was that you have to pick somewhere on the spectrum between simulating and optimizing. So you can't really devise a model that, you know, is an optimization model at the same time as a simulation model. So most of the computational runtime was spent simulating like occupancy behavior, and therefore it would have taken way too much time to optimize all of that, you know, to minimize carbon emissions, for example, from a retrofit. So that's what I got from mine.
Awesome. Thank you so much. We have a really wonderful questions in the chat, so I will start with one. I think that's for Maggie, if I remember correctly. Just wonder if the costs associated with active and passive actions are assessed and compared.
Yes, so obviously if you want to provide a good option for commercial industry, you would have to assess retrofit strategies both from an environmental standpoint and from a financial standpoint. However, the actual financial side of it was outside the scope of my particular study. So I was more interested in, well, not more interested, but I chose to focus more on the reduction in energy and carbon. But it's definitely something to be built on further, and I did list it in my recommendations for further work.
Great. Next question, thank you. For the oversizing battery storage option, just wonder if the potential further reduction of battery costs is considered. Would this significantly change the conclusion?
Yeah, that's a very interesting question, considering that the battery cost of lithium batteries have been decreased around 85% during the last decade, expecting to decrease more. In our case, we had two options when evaluating the overall cost, either to calculate the degradation cost based on the replacement cost after the end of life, which at this case we should consider the reduction on the price. But in that case, we have to have in mind when the battery will need to be replaced. And because in our case, we wanted to see what is the cost in each cycle, we decided to do the calculations with the current capital cost and get the results based on the available remaining capacity for each cycle. But obviously the results would be significantly changed, and that's the point when we have to consider also the environmental impact of the production, considering that a reduced cost may lead the users to choose a small battery without considering the fact that the changing the battery very soon will have an impact on the environment due to their production.
Thank you so much. Question for Avik. What do you think are the practical barriers to implementing roaming? And if you could say a bit more how roaming works, because I'm not familiar with it. I'd love to hear a little bit more of the how it works, and then what are the barriers to its implementation?
Sure. So roaming generally, and I'll use the analogy of mobile telephony. You can plug your electric vehicle into any charge point. At the moment, you have to have a subscription with a particular charge point operator, whether it be Source London or BP Pulse, whoever. You have to have a separate subscription for each one of those suppliers. With roaming, you just plug your car into any charge point, and you're actually billed centrally by what we call mobility service provider, which could be a domestic provider, it could be Octopus, it could be Source London, it could be anybody, but they maintain that contractual customer relationship with you and that billing relationship with you. As happens with when you're roaming with your mobile phone, you can go anywhere in the world, you turn it on, you make a call, you're not billed by the country, by the operator that you're registered on, you're billed by your home provider. So if you're Vodafone and you're in France, France Telecom will settle up with Vodafone, and Vodafone will then charge you. So that's how roaming works from a conceptual point of view. So and again, my background was in mobile telephony, and I built some of the standards around roaming in the early days. And the biggest barrier that I found, and I think that's what, and also having held some interviews with some of the stakeholders within the electric vehicle charging industry in the UK, one of the biggest barriers is actually getting people together, getting industries to getting companies together, because everyone has their own commercial agenda. So when you get people together trying to standardize, trying to work together to build a virtually homogeneous network, everyone tries to put in their own agenda forward, because obviously it benefits them commercially, to some extent. So it's trying to get that way. It's the discussion, getting them together, agreeing on a standardized set of technologies and business processes as well. This is the business process that's the key sticking point. The technology exists today. The technology, the OCPP standard, which is based on what we call the ISO 15118 standard, does actually exist. It's currently at version 1.6. which does support roaming, and in 2.1, version 2.1 will actually automate that for digital certificates, and also bi-directional charging, so you can also charge into the grid for things like vehicle to grid services. So the technology exists today, it just needs to be put together like a Lego brick, put together in the right way. But it's more about bringing all the stakeholders together to understand that actually, and this is something I heard on a podcast a while ago, and I think is a great statement, to move fast, you move alone. To move further, you move together. Okay, and that's the challenge, is getting them together. And if they can't get them together, then there'll have to be a policy intervention. And I think the UK government will have to step in and start to mandate this as part of the wider plan for electrification.
How likely do you think is it to happen?
In terms of what, the industry comes together or the policy?
Or either one?
Either one. Well, they've already started. So there are companies like Electric Juice, which is a subsidiary of Octopus Energy. They've already got their product, the Electric Juice, one card, multiple providers. There's a company called Hubject, a German company that has a roaming hub, so you can connect to Hubject and you can then connect to anybody who is connected to that Hubject hub. So it's happening, and I think it's likely because it's happening quite quickly in places like in Norway, where it's actually it's mandated as part of a policy. In the Netherlands, there's a lot of growth in roaming, so that's happening very quickly. And then, so if you look at two case studies, Netherlands and Norway, it's happening. So I believe that it's likely to happen, because I think by looking at the economics, the cost to build a homogeneous network that crosses the whole of the UK are huge. And so they'll have to, to improve profitability, they'll have to start to collaborate if they're not going to start buying up smaller companies.
All right, thank you, Avik. Maggie, another question for you. How do you expect climate change will affect the efficiency of? Oh, wait, that one you already. I know. Will affect the efficiency of active and passive technologies, respectively. Is that clear?
Well, yeah, that's clear. Well, as my project focused on 3 specific passive and 1 active, I can answer for those. And since the use case was central London, I think the projected effect of warming climate is an increased risk of overheating in buildings. So the strategies I chose, for example, the external wall rendering, I did that to sort of create a protective shell or barrier between the exterior and internal environment. As looking at, for passive strategies, if you think of vernacular architecture that basically run off passive strategies are some of the most efficient natural buildings you have. So I think learning from that could be very helpful and beneficial in trying to combat the effect of a warming climate. And that's also why I chose to simulate a green wall facade, because greening, definitely in central London, has been proven to really help combat the heat island effect that we are experiencing more and more. Whereas the active strategy I chose by exchanging gas-fired boilers for an air source heat pump, I chose that as in future that could also be used in reverse for cooling, which a supermarket currently does not have any mechanical cooling systems in place. So that would help with more of the symbiosis between the subsystems there. So I try to choose them with like climate resilience and their mitigation adaptation potential in mind.
Great, thank you. Now we have 2 questions that are kind of general, and so I'll ask them to each of you again. The first one is just to make sure we're all on the same page. Is the definition of net zero the same for all the presenters? So you might briefly state what your definition of net zero is, if you think there's any discrepancies. And then as you're answering that, also if you can answer another question, which is, what do you think the role of consumers in the decarbonization process is? And that's, in a way, you've all highlighted, or most of you have highlighted more technological types of solutions and less behavioral solutions. So is there some behavioral solutions? Do consumers or behaviors have a role to play? So again, what's your definition of net zero? Is it different from the others? And what's the role of consumers and perhaps behaviors in the decarbonization process? So should we go in the same order again, if you don't mind? Maggie, oh well, Maggie, no, you just went. we'll go in reverse. Chris first.
Fine. Yeah, I believe we all do have the same definition of net zero, which is that all of the carbon emissions that we're releasing into the atmosphere are somehow captured as well. So there's net gain in emissions. I believe we all use that definition. So, and it's the goal is to achieve that by 2050. So that's sort of the timeline that we're all working towards. The second question is, yeah, so I'll respond with specifically to the work that I did. So I think, you know, all of us are residential consumers, right? We all are fortunate enough to live in, you know, with a roof over our heads, and we consume electricity and gas, or not gas if you're, you know, somewhere else, but, you know, we consume in the comfort of our homes. So I think what a consumer can do, mainly as a residential consumer, is to be an active participant in letting their residential consumption habits be something like publicly known. So one of the main limiting factors of my work was that most people don't want other people to know how they consume electricity or how they consume gas. But this data fundamentally drives consumption. Like, it allows more data to be synthesized. You can create more activity profiles that detail different patterns, like, you know, you cook around meal times, you know, watch TV at night, those sort of things. You can build a sort of an idea of how or when to expect, you know, peak demand, for example. It tends to be that everybody in the morning, that's when they have their coffee, so that's when they boil the kettles. And kettles, that everybody knows, is a huge consumer of, well, it creates a huge peak, and we should be expect that in the morning. But we only know that because people share that data. So I guess the other thing to do is just to increase their awareness as consumers. That I brought this example up to many people, but as we consume you know, energy in our homes, we're not always aware of where energy goes to waste. So if you're boiling 1 cup of coffee, don't fill 5 cups of coffee worth in your kettle and then leave four cups worth to just cool down. Or if you're taking something out of the fridge, don't open the fridge and then go, wait, what am I taking out? Just you can think about it beforehand, and these things sort of they add up over the course of weeks and months and years. So that's what I would say from my point of view.
Great, thank you, Chris. So we're going backwards. So Ilya.
Yeah, I think with regards to the net zero question, we're all going to agree on that definition. So I'm going to skip over that part right now. But yeah, I definitely think the role of consumers is a big one in the decarbonization process, specifically so we can have a holistic understanding of all the different use cases, you know, of how individuals use these technologies, and in my case specifically EVs and the public charging infrastructure. So kind of a big reason I decided to do my research on Alaska, besides basically being from there, is because the literature really has a lack of diversity of use cases for EVs. You know, they've been mainly focused on these highly urbanized, densely populated areas, which is not what Alaska is. And so kind of that does create a bit of an imbalance in the transition to electrified transport and the decarbonization process in general. So for me, it was really important to kind of capture the individual experience and behavior of Alaskans, which in and of itself is pretty unique, right? And that went a lot into the modeling process that I did. So for example, I looked at both summer and winter environmental behaviors and how that might change things. I looked at both weekday and weekend travel behaviors because Alaskans really like to go hiking. And if you only considered, you know, weekday behaviors where you're driving your kid to school, you're going to work, you're maybe going to a commercial area, that drastically changes the utilization of the public infrastructure. In my modeling specifically, I found that 86% of charging on the weekday occurred at home. So the public infrastructure was really not used. So if you're basing your decisions off of that, which is just a subset of travel behaviors, you might not get the whole picture. So I think understanding consumers and how they would actually utilize the infrastructure, what their behaviors are, is very critical to the decarbonization process.
Thanks. Just to follow up on that, you of course, a lot of your conclusions revolve around this hiking behavior that you identified. And I know Canadians like hiking, but how representative is your sample that you can actually say that that's something that's really relevant for the general population? Because this is based on data you collected yourself from interviews, right?
Yeah, it's data I collected from interviews and from surveys. So, my survey sample size was about 215 individuals, which is close to 10% of the population. So in that regards, I would say it's pretty representative, as well as just having anecdotal information from other people also tells me that that's something that occurs pretty frequently. And also with regards to hiking or recreational travel, a lot of that actually doesn't directly relate to things like hikes. It also relates to things like personal use fishing or hunting, which is things that a lot of Alaskan residents do. And those kind of travel behaviors tend to encompass distances that are much larger than those on the weekday. So if we're really trying to decarbonize transport in Alaska, those are definitely things that we need to consider.
Okay, but how did you, so the sample size is one thing, but how you recruited your sample is another thing. And I fully agree and the Canadians are very outdoorsy, but I wonder if that's still representative that you compare with. Can you tell us just very briefly your recruitment strategy, and if you compared with activity surveys that are representative of the population?
Sure, yeah. So the recruitment for my survey was done entirely on Facebook. So basically anyone that was a resident of my case study, so the municipality of Anchorage, could have received my survey. And basically I got a pretty diverse group in terms of education level and age. So I was pretty satisfied with that. I also did want to get more EV drivers for the survey, but unfortunately that sample size was extremely small. So I got, I think, about 20 EV drivers for the survey, which really is fairly insignificant, which was unfortunate. But in terms of getting a good sample of the population, I know I didn't get a good enough sample to residentially describe the population. So one of the purposes of my survey was to actually accurately describe where an individual would live compared to where they would go to work, specifically for the model. But in that sense, it was not representative. But I think in terms of activity types, it was.
Okay, thank you. Great stuff. Avik, do you want to go next?
Yeah, hi. So just taking the net zero in terms of definition, I mean, in terms of my project, it was really focused around the use phase, the use phase. So it didn't look at the manufacturer of the vehicle, nor did it look at the electricity source, the generation source. But obviously, we need to look at it end to end in terms of the life cycle. And there are vehicles coming out, like from Volkswagen, like the ID3, ID4, which are claiming to be net zero based on a life cycle analysis of the cradle to gate analysis. So. And you know, the generation side is slowly decarbonising, but fundamentally, you know, on the use phase side of things for personal transport, we do have to shift towards electric vehicles just because of the deadlines that have been set by the UK government, but also because we have to do it now. The point is that, and it's leading on to consumer choice. I mean, I think the point of my study was to really provide some levers to incentivize industry and the consumers to shift faster to electric vehicles faster than it's happening today. So, you know, if you're, you know, rural residents or people who live outside of major urban centres will always have to rely on personal transport because the public transport system in the UK just isn't set up to feed their needs. So they're always going to be a sector of the population, a large sector of the population that needs personal transport. And so therefore, we need to start, you know, to accelerate their transition to electric vehicles by providing ease of access to charging points and also incentivizing them on cost. In the urban areas, it's going to be, I believe there's going to be a more of a decline in personal transport. There'll be a modal shift towards public transport. Also, new developments will start to not have parking facilities. You know, they'll start to have bike sheds and what have you. They won't have parking spaces. So then it's about consumer choice. So, you know, there are two choices to be made, you know, by a hybrid or an internal combustion engine versus an electric vehicle. That's the first consumer choice, and that's going to tend to be the choice that's going to be made by people who have to do longer distances, i.e. rural inhabitants. And then there's the other choices, do I have a car or not? You know, and that's going to tend to be a choice coming from the more urban areas. So it's more, for me, it's more, you know, in terms of my project, it's more about consumer choice. And that's what's going to really drive the decarbonisation of personal transport.
Great, thanks. I'm happy to hear you also focus on more rural areas and urban areas, given that in urban areas it's definitely also an opportunity cost to be investing so much in electric vehicles when there are alternatives that can be pushed and have greater impacts, as you all know from the class I taught you. So thank you, it's good to hear that. Next is Dispo.
Yeah, as for the net zero, I want to add on what Avik perfectly said, that it's not just about avoiding the emissions with the shift on electrification and the integration of renewables, but we also have to consider to balance actually the capture of the emissions that are associated with the production of those technologies. And in my case, about batteries, that we saw that they have a great impact on the overall emissions. And as for the occupants' behavior, the consumers' behavior, in the case of buildings, the occupants' behavior, it's really important considering that the consumption profile is based on the use of appliances and their thermal preferences. So we really affect the decarbonization process. And here we should mention also that in the case of integration of electric vehicles to buildings, we have to, the occupants should trust the fact that this integration and even like the vehicle to building integration will have to the battery life of his vehicle. So it's important to also to gain trust in order to take the right decisions following the path of decarbonization.
Thank you. Mira, next.
Yeah, so for the net zero definition question, I think my answer is pretty similar as as my teammates. And in terms of the consumers, I would say from a general perspective, they provide us the information of which sector is urgently requiring decarbonization. Like the heating sector accounts for a large portion of the total energy consumption and carbon emissions, and that's why I decided to conduct my project. And also, I think as the customers are kind of terminals, when we are designing the specific energy systems, we should always based on the local consumption needs. So in terms of my study, I changed the boundary conditions such as the environmental temperature and the required water temperature to see how the system performances under different customers' requirements. And I will also say that the customers' requirements are usually kind of customized. So that's why when applying certain technologies or popularizing certain technologies, we should always investigate whether they're actually suitable for the specific conditions. Yeah, that's it.
Thank you. And we are running out of time, but I want to let Maggie have the concluding word. Go ahead, Maggie.
Yeah, I'll just jump straight into what customers or consumers can do. Definitely in a supermarket setting, I think it's quite clear that if customers were actually able to open a door to a fridge to get the product they need, then the supermarket energy demand would reduce greatly, and also the thermal comfort felt would enhance. I think that would be a win-win if consumers could only open a door. Hopefully that we'll see that soon.
Thank you so much. It's been fascinating. Sorry we're a minute late. Back to you, Nadia. Thank you.
Thank you, Dr. Audrey, for your leadership in that discussion, and thank you to all the panelists. That was amazing. Our second session is on low carbon technological development. So I'll just hand over to the team for the presentation.
Good afternoon to all the virtual attendees of the SEF conference of 2021. My name is Camille Plessis, and on behalf of my colleagues in this low carbon technological development group, I would like to thank you for taking an interest in our research topics today. The main objectives of our presentation is to show the viability and feasibility of promising low carbon technologies. In other words, we will present the options for future low carbon technologies and ways to implement and develop them in an efficient manner. Indeed, innovative and viable technologies are key to accelerate the energy transitions toward net zero by 2050, but the rapid and efficient development of these technologies will not happen without the help of development tools such as profitability studies, hybrid system optimization, or model sensitivity analysis. Whilst each of our innovative research topics is unique, our group will therefore try to enlighten you on some promising new technologies, but also to inform you about tools that could facilitate their development. To present our research in an intuitive and cohesive manner, this presentation is structured in 3 parts. In the first time, our technology specialists will take the lead on their subjects, answering the question, what are the promising low-carbon technologies of the future? It will start with Alex, who will talk about a luminescent downshifting material to enhance the efficiency of hybrid photovoltaic and thermal solar panels. Following this, Magali will look at how biomethane can be made more sustainable by incorporating regenerative agriculture practices in its supply chain. In a second time, our economic specialists will try to answer the question, how can we make these technologies profitable? Sasha will deal with improving the profitability of green hydrogen projects, and Max will investigate the different options of hydrogen production from floating wind. Last but not least, the developer team will dig into different ways to facilitate and accompany the development of new technologies, answering the question, how can we make their development happen? I will address methods of global sensitivity analysis applied to offshore wind industry models, and then Hector will talk about optimization of hybrid systems. If you do happen to have any questions, there is an opportunity to ask them at the panel session, which will be taken place following the conclusion of these presentations. So now, without any further preamble, Alex will begin our presentations.
Thank you, Camille. I will be discussing how academic innovation and exploration stimulate progress in the context of hybrid solar energy. I'll begin by discussing what the appeal is in using hybrid photovoltaic thermal systems. So to start, the module uses both photovoltaic and solar thermal harvesting principles simultaneously. So the PVT module can co-generate electricity and thermal energy. This provides enhanced energy efficiency compared to a standalone PV. Some configurations have even achieved efficiencies above 80%. However, much of this efficiency is achieved through the thermal collector, and the PV efficiency is curtailed due to thermal coupling. However, there have been many innovative optics studies that mitigate the reduction in electrical efficiency. Spectral beam splitting technology uses optical filters to segment the solar spectrum and deliver 2 different ranges of light to separate locations. This not only enables a thermal decoupling of the system, but also provides more efficient capture by the PV module. Radiation with energy below and much greater than the band gap is converted inefficiently and leads to heat generation and degradation of the solar cells. SBS can filter and redirect these ranges of light to the thermal receiver in order to augment the PV performance. There are many methods of performing SBS. One innovative technique that has directed this research is using liquid filters, such as nanoparticles suspended in a base fluid. Nanofluids have unique optical properties that can absorb and transmit light at different wavelengths. And due to it being in a liquid state, it can also absorb the light in the form of heat and transport it for use directly. It can also cool the PV by flowing cold fluids underneath the PV prior to interacting with the solar spectrum. This design is quite ingenious and solves multiple challenges simultaneously. This research study used luminescent downshifting materials rather than nanofluids. LDSs have extremely unique optical properties in that they alter the wavelengths of photons they interact with by increasing its wavelength. A schematic on the bottom of the page illustrates how this process occurs and why it is so special. When the LDS absorbs the incoming photon, lambda x in this case, an electron is excited to a higher energy state. This electron then relaxes in a piecewise fashion to emit 2 photons of light at a lower energy. Of course, conservation of energy must be maintained. However, this is an extremely powerful technology for PVs because the module can not only reduce heat generation by converting photons closer to the band gap, but also convert more photons, essentially increasing the efficiency and lifetime of the module. The graph on the right shows the effect on the solar spectrum before and after interacting with an LDS dye. It is evident that the dye absorbed the radiation at 500 nanometers and increased the radiation at around 700 nanometers. Due to a lack of literature and experimentation on the topic, it was decided to investigate the use of LDS dyes as a heat transfer fluid and optical filter for hybrid PPT. The experimentation was executed using MATLAB simulations, testing for 3 different efficiency criteria and used 5 LDS dyes compared to a standalone cadmium telluride PV. However, I will only be discussing the 3rd efficiency criteria today. This condition was simulated in standard testing conditions and displays the effects of the PV efficiency. 4 of the 5 dyes outperformed the standalone PV, and the V570 dye achieved more than 15% improvement in the standalone. In conclusion, this research shows promise and warrants further investigation by replicating the results with a physical module. This research was aimed at improving solar efficiency and innovating new harvesting technology. Scientific research and exploration leads to advancements in technology, and moreover, enhancing solar energy technology will lower the cost of energy production and streamline the transition from fossil fuels to renewable alternatives. The research performed plays an essential role in the early development of renewable technology and ultimately the commercialization of it. These principles are seen across the entire renewable industry, and Magali will now discuss the biomethane production and its environmental impacts.
Thank you, Alex. So, like photovoltaics, bioenergy is another way of using energy from the sun. Biomass is produced via photosynthesis and can then be turned into biofuel. Here we'll look at biomethane, a promising renewable alternative to natural gas. It's produced from biomass, which can be any form of organic matter, including food waste, animal manure, and crops. These are anaerobically digested by bacteria, which produce biogas, a mixture of methane and carbon dioxide, and this can then be upgraded to biomethane and injected directly to the natural gas grid without any need for network upgrades. It's been shown that using organic waste is a very sustainable way to produce biomethane, but the potential for expansion is limited. To rapidly increase capacity, operators are turning to energy crops such as maize as feedstocks. But is this sustainable? To answer this question, a life cycle assessment of biomethane production from maize using conventional agricultural practices was carried out using real data from a biogas and biomethane operator. This graph shows that the global warming potential of biomethane from maize is similar to that of natural gas and can even be much higher in the worst case. What's more is that even the best possible result does not meet the requirements of the Non-Domestic Renewable Heat Incentive, or NDRHI, or that of the New Green Gas Support Scheme, or GGSS, which are subsidy schemes in the UK which promote the production of biomethane. Life cycle assessment is a useful tool to understand the main environmental impact drivers. Looking at the global warming potential of different stages of the biomethane production process, we can see here that the 2 most significant drivers are the agricultural phase and the anaerobic digestion phase. There are limited options for reducing the anaerobic digestion impacts, so reducing the impact of maize production is key. So how can we do this? Well, one option is regenerative agriculture, which is an approach to agriculture which seeks to restore and improve ecosystem health. Practices include reduced tilling operations to minimize soil erosion, using organic over synthetic fertilizers, and using sequential cropping over annual cropping to ensure the soil is never bare. These practices can improve soil health and also lead to carbon actually being sequestered in the soil, and both of these things will help to reduce the environmental impact. Sensitivity scenario analysis was carried out to find the optimal combination of regenerative agricultural practices to minimize the global warming potential footprint of maize production for biomethane. Applying these practices to the maize production process gives a 31% decrease in global warming potential compared to biomethane from maize produced using conventional agriculture, and a 33% in global warming potential compared to natural gas. This is a big improvement, but it can be seen that's still not enough to meet the sustainability criteria of the Non-Domestic Renewable Heat Incentive or the Green Gas Support Scheme. However, these are still encouraging findings, as biomethane will generally be made from a combination of feedstocks, not just maize alone. By combining maize with organic waste, a much lower global warming potential can be achieved, and so it's been found that growing maize as an energy crop using regenerative techniques can contribute to a faster, more sustainable expansion of the biomethane sector. However, it is important to highlight that the reliance of biomethane producers on subsidy schemes, such as the ones we've seen here, show that this technology is not yet profitable, as is the case with many developing renewable technologies. So Sasha will now talk about hydrogen, another promising replacement for natural gas.
Thank you, Magali, and thank you, Alex, for introducing several emerging low-carbon technologies. Yet, it is essential to understand that to reach a large-scale implementation, cost competitiveness and high profitability must be achieved. Thus, economic criteria should not be set aside. Another low-carbon solution that we're hearing a lot about recently is green hydrogen. Hydrogen corresponds to a gaseous molecule that can be qualified as green if it is produced via water electrolysis and uses renewable electricity. This low-carbon solution is in opposition to grey hydrogen that is produced from hydrocarbons and emits large amount of CO2. The green molecule is expected to largely contribute to reach net zero by 2050, as it is predicted that it could supply 22% of the total final energy demand. Yet, it is barely used these days, as grey hydrogen is currently 3 to 4 times cheaper than green hydrogen. As no end user will accept to pay a higher price for a greener technology that satisfies the same need, low carbon technologies and specifically green hydrogen must become cheaper. The option to increase profitability investigated in this research is to use the technical properties of the electrolyzer to perform grid balancing services and generate extra revenues. The idea of using grid services to enhance profitability is not new, as currently in France, industrial with large electricity consumption already perform such services. To ensure an optimal operation of the electricity system, the transmission system operator, called TSO, constantly balances supply and demand. If demand is too high or supply is too low, an imbalance appears and can lead to network failures if the balance is not restored. To do so, the TSO pays large electricity consumers to reduce their electrical consumption and regulate the mismatch. As medium-sized electrolyzer has the same annual consumption as 2,000 households, such a device can participate to the grid support markets. Having expressed the potential path to increase the profitability of green hydrogen production, the electrolyzer could both produce green hydrogen for end users and vary the electrical consumption to support the grid and generate extra revenues by entering 3 different markets: the primary reserve, the secondary reserve, and the capacity market. To quantify the economic benefits of such a business plan, a techno-economic model was developed. Considering several sources of renewable energy supplying the electrolyzer, a sensitivity analysis was performed to understand which configuration of grid balancing services could benefit the economics of green hydrogen production. The obtained result demonstrated that grid balancing services can increase the profitability of green hydrogen. Combining the 3 services generates extra revenues and so increases internal rate of return up to 38% for solar-based projects. In a more comprehensive way, this plot shows the benefit of grid balancing services on the resulting selling price of hydrogen. It here appears that 1 kilogram of hydrogen can be almost 50 cents cheaper if the electrolyzer is used to support the grid. In conclusion, profitability assessment can promote the production and use of emerging low-carbon technologies. To increase the profitability of green hydrogen and help reaching net zero at a decent cost, hydrogen producers should support the grid using the electrolyzer, as it can increase profitability and cost competitiveness. And governing bodies should design regulatory frameworks that promotes large-scale implementation of green hydrogen, but also of low-carbon technologies. Even though such a business model can enable the emergence of a self-sustaining green hydrogen sector, it is far from being the only option to be considered. And Max will detail a specific solution to improve economics of offshore green hydrogen production.
Thank you, Sasha, for your summary of green hydrogen profitability. Similar to Magali's biomethane technology, the flexibility of storing energy in a molecule over electrons has numerous advantages, particularly for industries, long duration storage and long distance transportation. As Sasha mentioned, this has led policymakers, researchers and commercial organizations to view the energy vector hydrogen as an essential component when considering whole system decarbonization. Hydrogen from offshore wind is the leading candidate for hydrogen production for northwestern Europe. Fixed bottom offshore wind turbines are utilised when coast to shore. In contrast, By 2030, floating wind will become near cost competitive with fixed bottom offshore wind and can be positioned further from shore to achieve higher capacity factors. For these longer distances, floating wind requires efficient transmission systems. Moreover, multiple benefits to electrolysis can be hypothesized when combining with floating wind. Therefore, the main aims of this research project were to investigate the techno-economic viability of different transmission methods for hydrogen production from floating wind and to explore how the input parameters impact the financial viability metric, the levelized cost of hydrogen, through a local sensitivity analysis. 3 pathways were designed for the research based on industry reports. Pathway 1 included high voltage electricity cable transmission to onshore electrolysis. Pathway 2 had centralized offshore electrolysis platform with hydrogen pipelines to shore. And similarly, Pathway 3 had integrated electrolysis at each turbine with hydrogen pipelines to shore. To compare the pathways, a techno-economic model was developed to estimate the cost of hydrogen over each pathway's lifetime. The discounted cost model inputted the associated energy losses and efficiencies to produce the hydrogen production per year. Then the costs in the project capex, opex, and decommissioning costs were used and discounted to create the levelized cost of hydrogen. Comparing the pathways, the electrolysis system integrated at each floating turbine was found to be the most viable, with an LCOH of £3.51 per kilogram of hydrogen. The figure presented here shows the different key parameters that have been varied in the sensitivity analysis and the range of LCOH the outputs cover. First, notice that the distance to shore is not the most important factor when considering the viability of a project. Other parameters such as floating wind capex, electrolyzer efficiency have more potential to reduce LCOH, so should be prioritized. Second, the search for the best resources it is worth it to find better capacity factors, as floating wind capacity factor has a greater impact than distance to shore. The circle here leads on to my conclusion, and the conclusion from the research was there's an independent confirmation of findings from the first pre-commercial dedicated hydrogen production project from floating wind, and they confirmed a 70-kilometer distance to shore crossover between electricity cable, Pathway 1, and hydrogen pipeline, Pathway 2. I found a 66-kilometer pathway crossover. Furthermore, it was found that the LCOH strongly depends on floating wind capex and capacity factor and the capex of the electrolyzer system. The main recommendation for a commercial implementation is to implement decentralized offshore electrolysis at the platforms because it was the most viable found. And an example application is an industrial cluster in a suitable located area, utilizing its sufficient offshore wind resource at any depth. Additional considerations could be, such as Sasha mentioned, grid connection to optimize the sale price of electricity and hydrogen, or to utilize natural gas pipelines for hydrogen transmission. Camille will now discuss how local sensitivity analysis, like the one performed here, could be improved.
Among the tools that can help develop low carbon technologies, performing sensitivity analysis on models is essential and useful, as just shown by Max. But usually local methods are used, and I'm going to introduce you to global methods, which are more powerful, through the example of offshore wind energy models. Offshore wind is a rapidly growing industry as part of the renewable energy mix, and the energy market is driving the tariffs down in Europe and globally. That was due to new technology enablers with larger wind turbines and progress in the industry. To determine the tariffs and make value-based calculations, energy companies are using sophisticated energy models that have many input parameters and require heavy processing facilities to play different scenarios. One of the key metrics that developers want to calculate thanks to these models are the levelized cost of energy, LCOE, which represents the total life cycle cost relative to the amount of energy produced. And sensitivity analysis can be applied to these metrics in these models. But first, what is sensitivity analysis? It's a good practice to understand the weights of input parameters uncertainty in relation with output uncertainty. In other words, it helps answering the question, when and how does uncertainty matter? People usually use local sensitivity analysis, meaning that they change a bit the value of one input, setting the other ones, and look at the changes in the output. But what if there are interactions between inputs? Or what if the model has hundreds of inputs, as for offshore LCOE models, and the analysis becomes very time-consuming? That is why global sensitivity analysis methods appeared. There are statistic tools that can perform sensitivity analysis very quickly, taking into account interactions between inputs, and they can even help building meta models that simplify the model to run it faster without losing its behavior. However, they are still rarely performed, and this project developed a methodology to use global sensitivity analysis tools on energy models. Applied to offshore LCOE models, here are the results. What you can see on this graph are Sobol indices from 0 to 1 that rank the influence of inputs in the uncertainty of outputs. 0 means that the input has a weak influence on the output uncertainty, and 1 that it has a very strong influence. And we can see that only a few inputs impact the output uncertainty. In this case, wind speed, efficiency of the turbine, and operation and maintenance costs are the most influential inputs in LCOE uncertainty, and modelers should focus on them to decrease the inherent uncertainty in their models. In conclusion, global sensitivity analysis is a good practice and is a tool that could help developing low-carbon technologies such as offshore wind farms. It can provide value by verifying models. It provides deep explorations of how parameter, hypotheses, and interactions between inputs impact the outputs. In this case, it helped to verify the coherence of the model by giving results matching the theoretical formulas, for example. It can fix uninfluential factors, allowing a model simplifications by building a meta model that can run the model faster. Moreover, it can prioritize important factors by identifying very influential inputs in the output uncertainty, allowing, for instance, further data collection on this factor to decrease the uncertainty of the model results. For example, special efforts should be made to estimate the average wind and efficiency of the turbine in this project. And finally, it can support decision options by quantifying the sensitivity associated with the factors. Talking about models, Hector will now explain how optimization on hybrid systems is essential for the efficient development of low-carbon technologies.
Thank you, Camille. This project will introduce hybridization and optimization as tools to allow the uptake of renewable energies like the ones described by my team. The project consisted of designing a hybrid renewable energy system and determining the technology mix and size that optimize different performance indicators, with the case study of a hotel in Fayum, Egypt. A hybrid renewable energy system is a combination of 2 or more renewable technologies to improve the overall efficiency of the system, its flexibility, and energy management. The main drivers motivating the need for these systems are obviously energy poverty, that still affects millions of people, and the need to transition to cleaner technologies. However, hybrid systems are also driven by the challenge of intermittency that single-source renewable systems still face due to their unpredictable sources of energy and dependence on climate conditions. Hybrid systems allow to mitigate the effects of intermittency by providing energy security, reliability, and flexibility, and allows to bring renewable energy to off-grid rural areas. This project explored a mix of solar-based technologies like PV, solar thermal, and hybrid PV thermal panels, wind turbines, and biomass power technologies like biomass boilers and combined heat and power units. And although I investigated 2 scenarios in this presentation, on-grid and off-grid, I will focus on the off-grid system with battery storage to prioritize the need for these technologies in off-grid areas. However, the optimal design of a hybrid system depends on the application, the location, and most importantly, the stakeholder objectives. In a renewable energy project like the hybrid system for this hotel, there are multiple stakeholders involved, like investors, governments, the community, and even the environment. Each of these stakeholders is interested in optimizing the performance of the system with a different perspective. For instance, the investors will want to optimize the economic performance by minimizing costs, or the community may prefer to minimize emissions. Therefore, the optimal technology mix and size of the hybrid system depends on the objective to be optimized. To this end, I developed a model with MATLAB optimization toolbox where the optimal technology mix and size of the hybrid system can be obtained according to different performance indicators that represent different stakeholder interests. Examples of these interest indicators are economic ones like CapEx, LCOE, or payback time. Technical, like energy losses or efficiency. Environmental, like greenhouse gas emissions, embodied energy, or noise exposure. And sociopolitical ones like unemployment rates or landscape impact. The main challenge faced when optimizing a hybrid system was the presence of conflicting indicators. Here you can see an example of some of the results obtained for the energy mix and size of the system in kilowatts when aiming to minimize the LCOE, which results in a combination of solar PV and biomass boilers mainly. In this other graph, I show the results obtained when aiming for carbon footprint minimization, which returns a more diverse combination of technologies. It is noticeable, though, that optimizing costs results in high emissions and minimizing emissions involves higher costs. This is proof that economic and environmental optimization are conflicting objectives. Therefore, multi-objective optimization is essential in practice, as the best solution should satisfy most, if not all, stakeholders. An example of a multi-objective optimization is adding an emissions constraint to an LCOE optimization. This way, the user can find an economically optimal solution that also respects the environmental objectives. Comparing these results with the single objective ones, it can be seen that an intermediate solution may not be optimal, but good enough from all perspectives. This requires, however, flexibility and collaboration between stakeholders. In conclusion, the approach when optimizing a hybrid energy system consists of choosing relevant technologies for that application, identifying the stakeholders involved and their objectives, and finding an optimal solution and a balance between objectives. Hybridization and optimization are key to make the development of renewable technologies possible. The former helps mitigate the effects of intermittency and bring green energies to off-grid areas. The latter allows to optimize the design and the performance of the system. Both combined can accelerate moving towards energy transition and away from energy poverty. Finally, as a conclusion for this topic, let's recap the 4 key messages we aim to deliver. A sustainable future requires low-carbon technologies. However, as of today, around 64% of global generation still comes from fossil fuels. We have seen today that we already have renewable generation technologies like solar PV or offshore wind that are developing and decreasing cost in an astonishing way, and some other innovations like hybrid PV thermal panels and green hydrogen, which we will hear a lot about soon. Research is essential to continue innovating and progress to more and more efficient technologies to finally move on from fossil fuels. However, having the technology is not the whole story. We need technologies to be reliable, cost competitive, profitable, and sustainable over its life cycle. Therefore, we need tools to evaluate the performance of renewable systems from technical, environmental, social, and economic perspectives, like techno-economic assessments, sensitivity analysis, and life cycle assessments. This way, we can not only learn how profitable, reliable, and sustainable technologies are, but also where and how to improve. Moreover, we need to promote hybridization of renewable technologies. Sources like wind and solar have shown complementary time behavior, such that while during the day and the summer season solar is predominant, wind speeds tend to be higher at night and during winter. Combining complementary sources in a hybrid system and optimizing the mix and size of the technologies according to the application can increase the overall efficiency and flexibility and help bring green energy to off-grid rural areas. Finally, and most importantly, we need communication and collaboration between stakeholders, from governments to communities. A successful energy transition depends on the policy support from governments, the funds from investors, innovation from companies, and concern and action from the people. Quoting American football coach Vince Lombardi, individual commitment to a group effort. That is what makes a team work, a company work, a society work, a civilization work. Thank you all for listening. We will now happily answer any questions you may have.
Interesting set of conclusions. Thank you, team. To our audience, kindly remember to post questions for the panel using the chat function. And for the next panel discussion, Ruslan Galimov from GE Renewable Energy will lead. Thank you.
Hi, everyone. Thank you very much for inviting me to chair this panel about the new technologies. I'm Ruslan Galimov. I'm SAF alumni. In 2009-2010, I was graduated with this conference talking about new energy technologies. I'm very proud to work today in GE, where we promote new technology such as offshore wind, onshore wind, energy transition, storage solutions, and hydrogen right now. And it's really a stunning experience to look at what the pitches of the students were done. So thank you very much for that. I think that the way how we're gonna structure this panel, I was looking very carefully at the presentations, and it's really interesting subjects. So I have one question for each panelist, and if you would be able to answer, and then we'll take the questions from the audience. So general comment on the overall pitches that I was looking at the conference. Indeed, that's a very good overview of the new modern technologies that he was investigating, such as hydrogen, biomass, optimization of the different energy sources within the energy mix, and using some different tools like sensitivity analysis in order to evaluate the impact of those. So it was very interesting to hear topics about the offshore floating wind and how does it work in terms of reducing the carbon emissions. I was very pleased to hear about the biomass and about the solar panels. So it's a very good mix of the technologies, which is representing the future, right? So, and the course of the title, the title of the master is Sustainable Energy Futures. And every time when I talk with someone, I say, yes, this is the subject which I was studying for. And so PV, wind, hydrogen, those biomasses, those are going to be technologies of the future. And I was very pleased to hear this presentation. So first question to Alex. You was talking about the PV new technology optimization, and you mentioned that it was about 15% increase on the analysis that you've done versus the previous technology. Can you elaborate a little bit more on that, and why it's 15%, and what's the line of sight of getting this higher, the figure?
Sorry, just having a bit of trouble. Yeah, so absolutely. So the 15% increase is a 15% increase in electrical efficiency of the PV module. This is not including the thermal efficiency, and it's due to the temperature of the PV module being so much lower than the standalone PV, which enables a higher efficiency, a higher conversion efficiency. And this occurs because the optical filter also doubles as a heat transfer fluid that can cool the PV, and it can also reduce the amount of heat generation from UV light and from infrared. So yeah, so it just reduces the temperature of the PV.
And what's the line of sight of increasing this efficiency from 15% to up? Like, what the theoretical limit you're gonna get?
Oh, what's the theoretical limit? So the theoretical limit would still be for the electrical efficiency would still be the actually no, I'm sorry. We didn't study the theoretical limit, so I wouldn't be able to give you an absolute answer. But in theory, it could be 100% from what I'm imagining, because you could use downshifting materials and upshifting materials in order to standardize all the light to be at the exact band gap. Obviously, that's impossible because it just wouldn't happen in a realistic scenario. But yeah, it could definitely be above the Shockley quasar limit for single junction.
Okay, thank you, Alex. It was very good presentation indeed. So next question I have to Magali. It was interesting to hear about this 31% improvement of using the multi combination of the different technologies like fertilizers, like sequential cropping, and the other technologies. Question I had was, you mentioned that those right now technologies that you're promoting and you're talking about in your research, like there was a statement saying that it's not really profitable. Yeah, if you can just explain why they're not profitable and like what would make them profitable. And among the three technologies that he was looking at, which one is the most profitable and which one requires more, let's say, attention of the investments or improvements? Would be great.
Yeah, absolutely. So when I said it's not profitable, that's for biomethane in general. So regardless of what kind of agricultural practice you're using, biomethane is not profitable, and that's just because natural gas is so much cheaper. And that's kind of the product that it's competing directly against. And you know, biomethane can't be produced on such a large scale, so it doesn't kind of profit from that economies of scale like natural gas does. Like anaerobic digesters are like fairly small scale compared to that. So that's why it's not profitable. Things that would definitely improve the profitability of it is things like a carbon price. Obviously, if you implemented that, then compared to natural gas, biomethane would perform far better because the fossil greenhouse gas emissions would be much lower in comparison, even if they're not zero. And they're not zero from the project I presented because it's from maize. So you're growing a crop specifically to produce this biomethane, and so all your agricultural impacts add up in the life cycle system, and so the biomethane has still a positive global warming potential, even though it's reduced compared to natural gas. But actually what's really interesting is that if you look at other feedstocks, things like animal manures, they're waste, so there's no really impact tied to that, and actually you get avoided methane emissions, because if you digest those rather than just leaving them out in the field to further decompose, you have avoided methane emissions, and those can have actually you can end up with a life cycle global warming potential that's negative. So if you have something like that with a carbon price, then biomethane would definitely become more.
And this is what is going to happen, right? Because the companies which are producing the gas and the fossil fuels, let's say, now they're making some measures and publications about that they're going to be going carbon neutral, and this is somehow a kind of preparation to get this, this carbon, let's say, tax implemented. Maybe I skip that one, but like the sequential cropping, this is what was really interesting to me, and I had a feeling that it's the most profitable, that is most efficient technology, because like it's not adding some extra cost, but it's it could be kind of a technology. It's interesting. Like, do you have any examples? And would you consider that this is one of the most cost-efficient technology for now to improve the biomass efficiency?
Yeah, absolutely. I mean, from a cost efficiency perspective, perhaps not so much, because you still need the same inputs. You still need to put in the same fertilizers and stuff to grow your crop. Sequential cropping just means that instead of like leaving your land fallow for a certain period of time, you just plant your next crop straight away and grow it. So from a cost perspective, I'm not sure there's like major improvements to be found there, because the same inputs are still required. However, from an environmental perspective, that was the part I was really interested in. It has several benefits. So firstly, some people are kind of wary of biomass because it can cause this kind of food versus fuel dilemma. So where you plant these crops for fuel and then you're just pushing your food production elsewhere. By sequential cropping, you're avoiding that. So you're still producing your food crop, and then in the gap where the land would be fallow, that's when you plant your biomass crop. So you're avoiding that problem. And you're also, it's been shown that there's a lot of potential to build soil organic carbon. That's something I touched on briefly. So actually, by harvesting more biomass and keeping your soil covered for more of the year, you can increase the carbon content of your soil, so that actually, again, the net carbon balance is negative and the soil becomes a sequestration tool. So that's really interesting.
Yeah, indeed, it's very interesting. The biomass is it's interesting topic, because like just last year my son was asking me about what is the biomass, and because he studied this at school, and this is what is happening right now in France where I live, and what I'm looking at the reports and the potential of the optimization is really interesting to see how there are some ways to improve it, and the break-even versus the gas price is going to be solved somehow one day. So at this moment, the biomass is going to be one of the technologies which will help us to reduce the carbon footprint. Right? Thank you very much, Margaret.
Thank you.
So next question I had was to Sasha. Hi, Sasha. It was indeed interesting report on the hydrogen technology. And what I like the most is the graph that you was showing with different scenarios of with different scenarios of using. And a question I had to you was, like, you was using hydrogen wind kind of configuration. How about the did you look into the scenario where you will be using, instead of hydrogen, just the storage, like the battery storage as one of the scenario technologies? Because that's the question I had in mind right away, because this sixth scenario did not consider one of the most likely scenario which may happen in the industry.
So pretty much I was considering wind and solar, as you saw, but I also had one scenario which was considering wind, solar plus a battery to supply an electrolyzer. And I considered that, but it appeared that using only wind plus grid electricity was the most profitable scenario.
Yeah.
And in terms of the share of green electricity supplying the electrolyzer, this was using guarantees of origin, which currently appear to be not that sustainable at some point, but it is part of the subsidy scheme that the French government supports. And so it appears that you can produce green hydrogen using guarantees of origin. And using a battery could be relevant, but it is not profitable. And maybe at some point in the near future, and still with the aim of reaching net zero by 2050, it might appear to be not the most profitable, but the preferred option.
Yeah, it's going to be one of the interim solutions. And yeah, thanks, Sasha, for answering the question. And just to let you know, the one of the recent offshore auctions in Netherlands, it was about HKN project, I think, that the Shell has won. Company Shell, you all know the company Shell, right? And they were announcing the technology of the hydrogen together with the offshore wind, and they're working on this project as like they won this project, and there will be some already technologies installed in Netherlands in order to supply clean electricity, to get it through the electrolyzers, to generate the hydrogen, and to make those hydrogen plant like with the offshore wind facility. And this is like working in the offshore wind industry. I hear more and more about this kind of projects, and indeed the research that you've done is going to be very useful for the industry. So thanks for that. Yeah.
Thank you, sir.
Yeah. So we're going again to the same topic of the hydrogen floating. And Max, thanks very much for this indeed interesting topic about the floating, because this is really a hot topic today. And I was looking at the analysis. It was making a very good impressions of the analysis that you've done. There was all this sensitivity of the distance from shore, and the looking at how does it work in terms of what the capacity factor is playing for. A question I had, and this is because I'm working as a pricing leader, so I have these all figures in mind, etc. So, like, what technology of the floating did you consider? Because I think there are more than 20. And another one is like, what the capex did you consider, and what the variation of the capex per megawatt, let's say, or whatever you was considering as part of your model?
Yeah, so it's a really hot topic right now, and the combination of floating and green hydrogen is interesting, because you can put the electrolyzer on the platform itself, and there's only some floating platforms which will enable that. So I instantly cut out some that wouldn't enable that, and semi-submersible floating platforms have taken a really clear lead. And there's some research that says over 80% of the floating platforms that are available now, that are out there now, are semi-submersible. So they're taking a clear technological lead. They're becoming cheaper quicker than the other technologies, which is going to aid to it. But it was also the ability to put the electrolyzer system on the semi-submersible platform, which was the reason of that choice, and that's backed up by ERM's Dolphin project, which is a dedicated hydrogen supply project with floating wind, and they selected semi-submersible for that. And the capex is a tricky one, given I did a 2030 projection. So I was taking data from the offshore wind catapult and their project, their research on combination between offshore wind and hydrogen, and the variation of it was taken from multiple sources, and tried my best to get the best data. But there was a definite challenge in finding good data for this future time, and given the newness of the technology and the commercial sensitivity of the technology.
Right. Yeah, because you know that the floating technology right now is under development, right? So if I would be looking at like what I would take for the foundation model for the floating, I wouldn't find a really good solid reference on these figures. That's why you maybe have some difficult just to find these figures, because it's not like a monopass foundations or not like a jacket foundations where you have a lot of points of the data in order to make some kind of average. So, and right now the estimation of the floating wind foundations is really depending on the technology, and it's really depending on the type of the wind turbine, and this is where like the variation of the capex is going. But to let you know, there are many prototypes ongoing right now with different floating technologies, and on top of that is there are wind producers, the wind turbine producers, and they're collaborating with big energy players. Like in France, I've heard something with Vestas leading. I may be mistaken, and there are some projects in Asia about the floating. So there are some things going, and by 2030, we do expect that this technology may come as a kind of break-even level with a higher capacity factor and making this better for the industry itself. Because then
I think that's right, and by 2030, it will likely the technologies will start being more cost competitive. There won't be a big difference between the technologies, so the cost competitive. The ones that are leading will become more cost competitive with each other, and there's definite projects happening now. Total have a project called the Floating Power Plant, which is a wind wave floating hydrogen production facility for an oil and gas platform, which is happening today. The pilot project's happening today.
And that's the early phase of the development, because if you're looking at the offshore wind industry, even between the countries, like you're looking at the cost of the foundation in Asia, how do they estimate versus the cost of foundation, how it's happening right now in Europe, and like you see a multiply factor like of 2 at least, right? So this is what it would go down. It will be more cost competitive. We just need to get more prototypes running. And thanks for doing this research. It's really indeed interesting to look at the sensitivity analysis, and the result that you got was pretty much similar to what I think Camille was getting from the research on the sensitivity analysis. And I will pass over to Camille. Hi, Camille. The global sensitivity analysis, interestingly, it was also the topic which I also used in my master dissertation, and so I know this topic a little bit better than the others. And indeed, as I'm working as an energy expert in the world of the very complicated models, where you need to model the wind farms, the production of the wind farms, and the foundations, and those models sometimes made in Excel, sometimes are very heavy. They have like more than 100 inputs. They may be kind of very simple at the nature, but like realized very differently. And the global sensitivity analysis tools, which was done in the research committee, it's really interesting to see. It simplify the modeling overall, and it saves a lot of hours for the modeling. So if you can just elaborate a little bit, let's say, what tools did you use, because I did not mention that one in the research, and what the methodology did you use on this analysis, and if you can elaborate a little bit on those.
Yes, sure. So the software that I used was SoberGSA, which is a software that was developed by some researchers at Imperial College. So it's basically a software that implements several methods of global sensitivity analysis, and it's like you have to put your model inputs in it, and then it's going to apply it, and you're going to have some beautiful graphs and all the analysis that goes with it. Yeah. And the methodology that I used was to understand the model that I had, the LCOE model. Then I had to list all the inputs that I wanted to integrate in my analysis, and then I used this software with a MATLAB interface to get the analysis done. And yeah, that was mainly the methodology. And then I had to check. So I used different methods of global sensitivity analysis to check my results, to see if I got the same thing at the same time with different methods. And yeah, that's it.
Yeah, great. And I think that the result you've done is going to be very useful for all the energy models in the future. And and I think it gives a little bit more elaborations that you can do the optimization, you can build the metal modeling, and this is something which can be, your research can be used as a part of the other students' research for the future. That's great. Okay, so last question to Hector that I had, and apparently it's very matching with the question from the auditorium. Was he was doing an analysis of mix of different technologies within the sector and within the energy sector, and I found it interesting because indeed there are many reports talking about this, but like on the optimization from the different stakeholders' point of view, this is analysis which I see very rarely because it's all optimizing one or two factors, but that was multi-parameter optimization, which is indeed a very interesting scientific and also sustainable energy futures topic. A question I had, and this is exactly the question which I had from the audience, is was the COD cost been included in the LCE? That was a question from Tang Fei. And I had also a question on that one, like, did you optimize toward the CO2 optimization model? And was it properly counted? And like, was it multi-objective optimization or not? That's a question I like, mine and question from Teng Fei.
Yeah, so I saw that question, and actually I think it's a great suggestion because I think that's another way to have multi-objective optimization happening. But the thing is that I focus in this presentation in two main perspectives, economic and environmental. But actually, in my project, I explore also technical indicators, social indicators, etc. So applying that CO2, including the LCOE, would be very specific for that optimization. So by adding these constraints that I mentioned, I can do multi-objective optimization independently of the indicators that I'm exploring. But definitely is another way. If you're just doing a model comparing environmental and economic perspective, I think it's a good way to have both included at the same time by adding the cost you have to pay for the emissions. Definitely.
Right. Yeah. Okay. Thank you very much. Yeah, indeed, this optimization was a interesting topic to look at, and I think that we will need to look more in details on your posters and on the results available in the internet. Yeah, so I had some question from the audience, and a question to the moderator is like, do we need to publish them, or like they already published the questions, so I just need to read them all?
They're already published. You can just read them.
Okay, great. So the first question I had, and unfortunately it was not stated to whom, so I will address it to everyone. And it's what's the current TRL of hybrid PVT, and how much of the price of the per kilowatt hour do you expect from the system? And because of the combination of electricity and heat produced at the same time, how this power plant with all the associated system will be designed? I believe it's a question to Alex.
Yeah. So current hybrid PVTs are in commercial use. So the TRL of those current modules is high. It would be a 7 to 9. However, LDS, the combination of LDS technology and hybrid PVT is relatively new. There are only 2 papers that I've seen online that combine these two. So I'd give that a 1 to 3 in terms of technology readiness level. And then the price per kilowatt hour so I didn't study the price per kilowatt hour because it's very early on in terms of the research. But current hybrid PVT technology costs around 4 to 8 cents per kilowatt hour. And seeing that this provides extra exergy, I would say that this would advance that. This would reduce the price per kilowatt hour. And then question 3, because
of the combination of heat produced at the same time, how this power plant with all the associated systems will be designed.
Oh, right. Okay. So hybrid PVT is not necessarily a power plant type of technology. It's more off-grid type of technology, and for an individual user, you can use them in homes to heat areas or to heat water. So it would be challenging to use a hybrid PVT in a power plant, but you could use it with a heat engine. But with LDS, I see it being used as a decentralized power source rather than as a power plant. But yeah. Good question.
I might need to buy one for my house, right? So like I'm really interested to see what the price per kilowatt I think is going to be for the installed capacity. Maybe you have these figures, price per kilowatt, not per kilowatt hour.
Price per kilowatt I do not have, but just trying to think.
Okay, but as long as it's going to be not very much expensive versus the current EDF bill that I'm getting, it's going to be also good, right? 4 to 6 cents is going to be within a good range, I believe.
Yeah.
And with the efficiency of for 25%, right? You mentioned the combined it was 37, if I remember.
Combined efficiency?
Yeah.
Yeah, the combined efficiency is anywhere from 20 to 80, depending on what type of module you're using, because it's so wide ranging.
Yeah, great. I think I need to study this subject for my personal use, right? And it's interesting. Yeah. So another question, I think it's going to be going about students who was delivering pitch on the hydrogen. So how fast hydrogen system can respond, and can it technically be used for the primary response, which requires very fast delivery?
I can answer that. So technically, only PIM, so polymer electrolyte membrane electrolyzer, can perform such services. Also, it is important to acknowledge here that the research I was focusing on and the research I performed is focusing on the French grid balancing services, which, considering the primary reserve, it is much longer than in the UK, as it requires the device to respond in 30 seconds and to reach the nominal power in 30 seconds, which suppliers like electrolyzer suppliers like ITM Power, which I called, are able to deliver such electrolyzers. And one, actually it exists two projects in Europe, one in Germany called RIF-Hein, and another one which is called H2 Future in Austria, are both performing such services. So the answer to that question could be yes, electrolyzer can perform such services. But it also appears that in the research I did, electrolyzer should and must focus on secondary reserve because revenues are higher and because electrolyzer can reduce their load consumption, their electrical consumption for a longer period. It makes more sense for them and it's more profitable to favor the secondary reserve rather than the primary reserve, which should and could be favored by batteries.
Yeah, Max, anything to add on that?
Yeah, a little bit to add. I on the technical feasibility of that, and my conclusion agrees with Sasha's that a PEM electrolyzer has a less than 1 second response to set point changes, including a 75% demand changes. And primary reserve is usually less than 10 seconds. So in technical speak, I think that a PEM electrolyzer can definitely act as primary reserve, and my reference was from the National Renewable Energy Laboratory.
Yeah, great. Yeah, thank you very much for the answers. Next question is, I think, goes to Max. Have you ever considered the offshore green hydrogen production with wave or tidal energy converter rather than the wind turbine? And from your point of view, would it be possible to complete with floating wind turbine?
Yeah, so I didn't consider it, given the maturity of the tidal and the wave power technologies, but that doesn't rule it out. So I think an option for it to be included in the future of hydrogen production is in combination with floating wind. And as I mentioned, there's a project by Total and Technip FMC, two oil and gas companies, and the project's called the Floating Power Plant Project, and they have 9.5 megawatts of floating wind with 2 megawatts of wave power underneath, so a combination on one platform, and then a hydrogen electrolyzer and hydrogen storage on the floating wind platform. And this storage from hydrogen is going to act as a sort of hydrogen battery for a nearby natural gas platform. So it's going to provide continuous green power for them. But the thing is about wave and wind, it's good to have a combination of wave and wind because we're going to have different resources at different times. but in terms of wave or wind on, in terms of tidal and wave on their own, there's too many associated unknown costs associated with them. They have small supply chains right now and small economies of scale compared to offshore wind, because floating offshore wind can use normal sized offshore wind turbines which have good supply chains. So in my opinion, it's unlikely that they'll be able to compete in producing green hydrogen on their own, given the experience of what floating wind can do in the future. And it has already, in the pipeline, there's already 8.8 gigawatts of floating wind for the UK alone. It already in the pipeline, already in the works, and 53 gigawatts for global. So I think in terms of whether it can compete with it, it's very unlikely.
Yeah, thanks, Max. Just to add on my side is I'm based in the office offshore wind Nantes, and I think that apparently it used to be an office where the tidal energy technology was also developed. So I used to talk with the people who was in charge of development of this technology, and as you see right now, right, the offshore wind, including the technology from GE company, it is really like boosting. Like we're talking about multiplied gigawatt per year, while the tidal energy is really something remain a kind of a niche technology. So I agree with Max, it's something which is not yet developed well, and the offshore wind seems to be much more developed technology right now, which is going to be continue for the future in mix with the hydrogen. That's my personal opinion as well. Okay, so next question is, I think the question will go to Hector. If does it require more effective optimization tools to balance between multi-green power supply sources with different power production characteristics and traditional consumer profiles, quantum computing?
Yeah, for example, for the different power production characteristics, systems like the one I explained that has solar, wind, biomass, etc. They need probably converters, because there would be a mix of AC and DC technologies going on there. And also for the second part, my model was based on this case study for this hotel in Egypt. So I used known demand data, for example, that I knew beforehand for the whole year.
Yeah.
Only a more complex model would be needed to account for variable demands, or like this kind of more conflicting or transient demand profiles, for example. Fortunately, my model just focused on this particular the demand for the hotel, but I believe that you can develop a more complex model to have these dynamic inputs.
Yeah.
And also, if I can say just one thing, that going back to the PVT, the price per kilowatts, because it was also one of the technologies that I included in my model. And even though I was more focused on like the model itself, I found some values in literature that I used for my research, that it's slightly over £3,000 per kilowatt as of today from the literature that I found, which is probably some estimations, but yeah.
Thank you very much. Yeah, I think we're getting to the end of the question. So the last question I had from the audience, it's about, I think that we will ask one person to pick up this question, is what do you think about the role of national governments in enabling and promoting these something compelling technologies and the mechanisms? And I think we had Camille not answering the questions, right? If Camille, you can say something.
Yes, I mean, of course, the role of national governments is important, because this technology
Is it breaking up?
Not profitable at the beginning, and they need support, and they need subsidies, and national government can provide part of them, and so I think the role of national government. Sorry?
Yeah, I think it's breaking up.
It broke up a bit, Camille.
I don't
I
mind.
could,
Something.
I can add something quick before Hector says something, maybe. Yeah, I think we should let the LCOEs and
That's one last comment here.
Yeah.
We need to wrap up.
And sorry for me.
Uh,
I think she's gonna.
Yeah, I think we will need to wrap up because we will need to go to the next session of the conference.
Have a role to play in terms of strategy and.
Yeah, I think that. Yeah, the question to the moderator. I think we can wrap up the session. If you hear me well.
Yes. Thank you very much, everyone. That was a very interesting panel discussion. For the last question, I would recommend that someone in the team probably replies to that. You can post a reply to Gavin, who can publish it.
Yeah, that's great. Thank you very much for inviting for the session. It was indeed very interesting section, and looking forward for the next ones. And so enjoy the conference.
Thank you so much again, Rasmus. So we'll move on directly to session 3, which is on policy, markets, and governance. So over to the presentation. Thank you.
Hi, everybody, and welcome to our presentation on policy, markets, and governance. Reaching net zero in an economically, environmentally, and socially sustainable manner will require radical development of new technologies and changes in the way we live. The way in which we govern through policies, market, and regulation must enable a clear pathway to be built to achieve a just transition, whilst also recognizing the uncertainty in future innovation and development. Myself and my colleagues will present the findings of our research into the policies, markets, and governance that will be required to enable this transition. This presentation is divided into 2 halves, with Hapsari, Daniel, Paul, Anna, and Alicia presenting on the first half on sector and regional specific policies and market regulations required to enable the integration of renewables. Victoria, myself, Ariella, Julia, and Josephine will present on the governance structures to enable the development of the future energy system. Whilst we will be presenting on a range of different topics, there are 4 key overarching themes to our research: decarbonization and enabling key clear pathways to be built, decentralization, not only of the energy system, but of its governance structure, democratization of the decision-making, and digitalization, so ensuring that digital technologies add security and value. Each of the following presentations will incorporate at least one of these 4 dimensions. But first, I would like to introduce Hapsari, who will speak to the decarbonization policies required to get Indonesia to reach net zero.
Thank you very much, Anna. Well, climate change mitigation is a global effort that needs all countries to design a decarbonization pathway towards net zero emission society by 2050. As the world's 5th largest greenhouse gas emitter, Indonesia could play a significant role in combating global climate crisis. In the study, I tried to promote an escalation of Indonesia climate change mitigation commitment by exploring alternative pathways to decarbonize the energy system. Indonesia has been showing its commitment to reduce greenhouse gases. The latest climate pledge was taken in 2016 when Indonesia submitted its nationally determined contributions, or NDC, aiming for 29% emissions reduction below business as usual by 2030, or 41% with international support. But now the question is, will Indonesia set up a longer-term and more ambitious target to reach zero emission by 2050? And will we be able to achieve it? So for the current situation, several policies that might help Indonesia to decarbonize its energy system are still exist. The first one, Indonesia is still heavily relying on coal, mainly to support the grid, as there will be an additional of 27 gigawatt of coal-fired power plants by 2028, which will make up half of generation mix and increase 25% of greenhouse gas emissions. Second, the renewables target is still modest, with the target could be easily missed with poor implementation. Third, policies regarding transport decarbonization are still limited. The most ambitious one is 30% biofuel blending target by 2025. And fourth, the energy efficiency target is also insufficient. This study reveals that implementation of existing policies can lower the emissions 7% below the NDC target by 2030. However, if you see the black line in the left chart, the current policies will lead to a steady emissions growth at 4% per year and is clearly not in line with Paris Agreement agenda. Therefore, two alternative pathways, moderate and ambitious, are examined. Implementation of these alternatives will flatten the greenhouse gas emissions trend until 2030 before reducing further to almost zero in 2050. Several policies are assumed for these alternative scenarios to drive Indonesia towards low carbon energy system, such as from the technical aspect, Indonesia needs to gradually phase out coal after 2028 and transition to renewables, regulate the electric vehicle cell target, fuel economy standard, and also ban on fossil-powered vehicles by 2050. From the financial perspective, the government needs to enable the long-awaited feed-in tariff and carbon pricing mechanism, as well as redirect the investment flows by relocating the subsidies on coal to renewables. For the last but the most important thing is from the political side, as the government needs to scale up its NDC commitment and implement it consistently in national and local scale. As a conclusion, current policies are sufficient to reach NDC target, but stronger policies are required to drive the country towards deep decarbonization. In addition to this, innovation of technology such as true digitalization will further be needed to facilitate and ease the energy transition. So now I will introduce Daniel to explore how digitalization will play a role in decarbonizing energy system in European Union.
Thank you very much, Absari. Our conference is a perfect example that we are more connected than ever thanks to digital technologies. Even a few years ago, it would have been difficult for students from 3 continents spanning 12 time zones to join forces for this virtual presentation. Digitalization is a challenge, but also a massive opportunity for decarbonization. However, the emissions reduction potentials of digital innovations were so far mostly neglected in systematic research. Digital innovations are an ideal complement to more mature technologies for closing the emissions gap to net zero. My study demonstrates that 6 digital innovations can reduce greenhouse gas emissions in the European Union by 5% in 2030 and by 12% in 2050 relative to a reference scenario with medium ambition. Some innovations can scale rapidly in the short term, for example, telecommuting, while others need more time to unlock appreciable emissions reductions, for example, smart charging. In combination, the emission savings from the analyzed innovations can outweigh emissions from the power usage of information and communications technology before 2030. However, we can only realize these potentials when overcoming key barriers to diffusion and to sustainable usage. I would like to stress the risk of rebound effects. If digital innovations induce additional consumer demand, their emissions reductions may be compromised. These rebound risks are particularly high for smart climate control and for virtual business travel. To address key issues and to unlock full potentials, my study identifies 6 policy priorities. First, a more deliberative approach to decarbonization, supplemented by disincentives for high carbon behavior, can reduce the risk of rebound effects. Second, more harmonized regulation across EU member states can reduce barriers to market entry. These reforms are especially relevant for approval processes of autonomous mobility and automated air traffic management. Third, ensuring equitable access to digital innovations and equitable sharing of benefits will be a major challenge for regulation. Novel approaches will be necessary, such as the independent oversight of user data collection. Fourth, to unlock the value of demand-side flexibility, electricity markets need to be modernized. Potential initiatives include the standardization of real-time pricing for end users and reduced barriers to capacity and ancillary market participation. Fifth, information and communications technology is a key transport infrastructure of the future. This means accelerating the build-out of 5G, fiber optics, smart metering, and public charging. Finally, sustainable digitalization of end-use sectors relies on green electricity. Rapid decarbonization of power generation will be crucial to ensure that digital innovations provide net negative emissions. I hope that this overview could convince you of the opportunities of digitalizations in mitigation and of the value of proactive and collaborative regulation. Digital innovations can potentially reduce our reliance on negative emissions technologies on a pathway to net zero, not just in the European Union, but globally. I mentioned earlier that sustainable digitalization builds on abundant renewable electricity. In the next section, Paul will discuss the challenges we need to address to enable high shares of renewables in the electricity mix. Thank you.
Thanks, Daniel. Indeed, the decarbonization of electricity is a major challenge for the years to come. All the measures that Daniel presented to us must be supported by a greener electricity. But more generally, reducing the carbon intensity of the grid will help to decarbonize the electricity sector, of course, but also the transport and heat sectors, which are set to be electrified. To decarbonize the grid, conventional power generation must be replaced with renewables. However, a question that is raised today is how do we do this in the most cost-effective way possible? The subsidy schemes currently in place have enabled the development of a large amount of renewables, particularly wind power in Great Britain. But these subsidy mechanisms are sometimes considered too expensive now that the cost of wind and PV technologies have decreased, so their future is in question right now. Some argue for their complete overhaul, others simply want them to carry more market signals. In any case, renewable companies will be more exposed to market risks in the coming years. So the aim of this research project is to highlight the risks that renewable companies will face in a more competitive environment. The first major risk is about the price that renewables are paid for the electricity they produce. The overall trend of the electricity price is set by the price of gas, but it evolves on a daily, weekly, and even seasonal basis according to two variables: demand and renewable generation. The figure on the right-hand side of the screen shows the price of electricity as a function of demand and the proportion of that demand that is met by renewable energy. The higher the demand, the higher the price of electricity. It's because more expensive power plants are needed on the generation side. But also, the higher the renewable generation, the lower the electricity price. Renewables emit less carbon. They have very low marginal costs compared to conventional power plants. So they are used in priority to generate electricity. And when they do, the more expensive generators are not needed anymore, and the price of electricity tends to decrease. In situations where almost all the demand could be met by renewables, mainly in 2020, very low prices were observed and even negative prices. In conclusion, whenever renewables are generating, the electricity price decreases. It means that renewable companies are always paid a price inferior to the average price. The second risk is highlighted this time looking at the future. The government plans an ambitious development of renewable energies, and it can have a significant impact on the electricity price. Several scenarios are considered, and the price forecast results are presented on this figure. Two possible evolutions for gas and carbon prices are considered, numbered 1 and 2. And for each, 4 scenarios of electricity demand and renewable deployment represented by the different colors. Overall, the evolution of the electricity price is set by the assumptions about gas and carbon prices, resulting in 2 very distinct paths for the electricity price. But the impact of renewables deployment is still significant. Between the least ambitious scenario called steady progression and the most ambitious one called leading the way, there is a £5 per megawatt hour difference in 2030 for the electricity price. Such a difference is considerable for the profitability of a project. In short, the more renewables there are, the lower the price, the less profitable it is for renewables. This is our risk number 2, the cannibalization risk. In conclusion, two major risks have been highlighted for renewables. Their very presence in the mix reduces the price of electricity on average, but on top of that, they are paid a decreasing portion of this average price. Nowadays, renewable projects are protected from price fluctuations by government subsidies. But if these subsidies change or even disappear, this could pose major risk for the development of renewables and therefore the feasibility of achieving carbon neutrality in 2050. This is the main takeaway of the presentation. At the end of the day, renewable companies will have to learn how to protect themselves from this risk in the future. One way will be for renewable energy projects to enter into direct agreements with large companies that want to source greener electricity, and that's exactly what Anna will now present to you.
As the market shows signs of maturity, it is only natural that subsidies start to decrease. This transition implies that both generators and consumers are more exposed to the market prices volatility that Paul just told us about. This may jeopardize the deployment of renewables, as the risk of having projects whose profitability depends on market projections are not attractive to lenders. To overcome this, power purchase agreements have become a useful tool for both generators and consumers. The most common type of long-term energy supply contracts in the UK are physical PPAs. Under this type of deals, the energy is supplied through the grid, the buyer pays the generator for the supplied energy, and it also pays a fee to the grid for sleeving the energy. PPAs use diverse pricing structures that involve different levels of exposure to the wholesale market. For its simplicity and its hedging benefit, the fixed price index to the CPI structure has become the favorite in the country. To set the initial PPA price, generators use the levelized cost of energy, LCOE, which is the minimum viable price they can offer, while the buyers compare the PPA price to the wholesale market prices. Due to renewables' unpredictability, it's risky for generators to set an exact volume of energy that will be traded. The common practice is to set a threshold of energy volume that has to be delivered and procured under the agreed conditions. But what does setting that energy volume threshold implies for generators? The graph displays how the following conditions relate to the intermittency of renewables. When a maximum limit is defined, the sale of the energy produced above that limit can be secured within the PPA, but at a lower price. Yet, the difference between the PPA price and the lower price is assumed as a cost for the generators, as it is a lost value. A minimum limit can also be set. If this limit is not reached, the buyer must procure the missing energy in the market, and generators have to compensate the difference in price plus a fee to cover all the extra costs of such transactions. Contracts may be set with both limits, either one or the other, or none of them. To avoid mispricing, the extra costs that may result from setting such conditions must be accounted for in the LCOE calculations. A solar PV and an onshore wind in the UK were used as case studies to assess the conditions for projects under the country's market situation. The modeling showed that using PPAs on those projects resulted in an LCOE of around £52 per megawatt hour for solar and around £35 per megawatt hour for wind. As shown in the graph, such minimum viable prices are contrasted to the forecasted wholesale market prices and the prices of PPAs closed in the last year, which go from 57 to 60 pounds per megawatt hour for solar and from 44.5 to 48 pounds per megawatt hour for wind. For solar, having its LCOE so close to the prices in the PPA market means its profitability is restricted, as it does not leave a lot of space for generators to place with the prices offered and still be competitive when compared to other projects. In contrast, onshore wind has a lower LCOE that allows generators to have higher profits while keeping a low price that makes the projects attractive to the buyers and to the lenders financing the project. In addition, it was found that the PPA element that has the largest impact within the LCOE is setting a maximum limit. Therefore, generators have a decision to make: securing the energy, the sale of the extra energy generator at a lower price, or selling the extra energy directly on the market, accepting the risk of the price's volatility. These agreements are already viable and attractive in the UK. However, the market still has to mature to make them more competitive, boosting the further deployment of renewables and incentivizing buyers to engage in those long-term contracts. The effectiveness of this tool has been already proven in the Nordic countries, and there is no doubt that the future energy system will be supported by them. Nonetheless, There are other things that consumers can do to support their decarbonization other than procuring renewable energy. Next, Alicia will tell us more about it.
With an increasing focus on demand-side response, Anna has demonstrated that the changing market environments will impact companies across all sectors, indicating the need for decisive action. Continuing with the theme of decarbonisation, I'm now going to take you through the journey of a net zero economy through the lens of UK corporations. With UK businesses currently contributing to 18% of the UK's territorial emissions, and space heating accounting for 25% of the UK's heat demand, businesses with large property estates are challenged by heat decarbonisation. 90% of UK firms see regulatory risks to taking proactive climate action, showing a clear policy gap between expected emissions and required reductions. Now, whilst carbon pricing is widely seen as the main policy instrument needed to solve the climate problem, yet no tax that currently encompasses all UK sectors, a corporate mechanism that is becoming increasingly relevant is internal carbon pricing, whereby a company implements its own physical or theoretical carbon price. This project investigated internal carbon pricing and its effectiveness for a successful net zero strategy, whilst considering potential remedies to sustainable implementation barriers. Through a heat decarbonisation investment model, an internal carbon price of £50 per tonne was shown to greatly incentivise a business case across a property estate of 359 buildings, reducing paybacks from 47.5 years to under 11 years. An internal carbon price demonstrated clear financial benefits, with the now deemed attractive business case representing the opportunity for the organisation to reduce its Scope 2 emissions by 17.7%, unlocking environmental benefits as a result. Taking this analysis one step further and considering how internal carbon pricing has worked historically across the entire private sector, an analysis of data from the Carbon Disclosure Project found that with over a quarter of UK firms saying to have implemented internal carbon pricing, it was found to show statistical significance in reducing a company's emissions over a 5-year period when compared to companies that do not employ internal carbon pricing. However, a small sample meant that it was difficult to obtain a precise estimate of model strength, which further exemplifies the complexity of internal carbon pricing. Summarising the investigation with some interviews with net zero corporations, analysis of the government's communication around climate change was shown to be unsuccessful from a corporate perspective, with over 75% of participants garnering unsatisfactory views, claiming that UK policy lacks consistency and fails to provide the suitable decarbonisation pathways for a successful net zero agenda. The project ends with some recommendations. Firstly, to UK corporations, they should focus on implementation, setting a high-level roadmap within their net zero strategy. Ensure flexibility in your financing processes with a long-term objective in mind. And lastly, consider applying an internal carbon price. Whilst there is no correct internal carbon price, applying £50 per tonne could instigate behavioural change. And finally, to the UK government, to continue their net zero 2050 ambition, they must ensure that they bring businesses along with them on the journey. To do this, they must be transparent, consistent, and consider regulation that will spur innovative solutions. All projects so far have provided various insights into the market and policy dynamics, focusing on some emerging themes of decarbonisation and digitalisation across various geographical regions. I'll now pass you on to Victoria, who will explain the schedule for the second half.
Thank you, Alicia. At this midpoint, first we would like to remind you that you can ask our team questions at the end of the session, so please do submit yours at the provided link. But before we move to the second half of our session, we're going to take a brief pause. As a group, we have been in online classes long enough to know that we all need a quick break every 30 minutes or so. So we're going to give you just that, 60 seconds now. The clock has begun. so that you can stand up, shake it out, walk around, have some water, whatever you need to do. As you're taking this break, if you're still around, I'm just going to remind you why what we are talking about today is so important. In the earlier sessions this afternoon, our colleagues discussed possible transitions into the low carbon space that we can take, exploring technologies, processes, energies, and innovative tools that we can use. But if we don't address the overarching policy and market mechanisms, as well as the governance strategies in place, these tools and technologies will not have a pathway for implementation. This is an issue that needs to be addressed now, so that they can effectively operate in the future space. We identified these 4 unifying themes between our 10 projects that span continents, sectors, and regulatory ideals, because we believe that they summarize the values that need to be carried forward in our global energy transition. And with that, we've reached the end of our break. Welcome back. So let's get started with the second half of this session's presentations, exploring how governance can adapt to better manage our current system, investigating anticipatory and participatory future pathways it can take. This will start with my research on the greenhouse gas removal sector, from its emergence to critical mass. In the IPCC's 6th assessment report released last month, it was announced that without rapid and large-scale reductions in greenhouse gas emissions, limiting warming close to 1.5 degrees Celsius or even 2 will be beyond reach. This is the starkest warning to date, calling for a societal response. With emissions targets frequently being exceeded, it's increasingly recognized that there's a necessity to not only reduce emissions, but also remove greenhouse gases from the atmosphere. So what is greenhouse gas removal? Naturally, carbon is removed from the atmosphere through photosynthesis in plants. Greenhouse gas removal aims to replicate this natural process, but at a global scale, employing the many available technologies that you can see on the screen, ranging from biological to inorganic to engineered. With technologies improving, this technological toolbox is reaching a state of maturity, appropriate for implementation. But this implementation isn't happening, begging the question as to why. To understand this better, this research used qualitative methods to analyze greenhouse gas removal in the UK and the US, 2 leading nations within this global sector. In the UK, greenhouse gas removal is undergoing a recent emergence, in part thanks to the Prime Minister's announcement of a 10-point plan for green industrial revolution. With this, strategies have been developing within government departments of business, agriculture, forestry, industry, and foreign policy, with funding mobilized for several preliminary projects. Also, launch of the Coalition for Negative Emissions in the commercial sector is placing pressure on the demand side. In the US, this situation is a little different. With national climate commitments only announced at the start of this year, the US is on a delayed removals pathway. The complexity of the US political landscape means strategy is developing at multiple levels, at federal, state, and voluntary levels. Climate action is restricted by bipartisan politics, and in consequence, the sector is growing closely aligned to the existing national fossil industry, with the majority of activity focused around point source capture. This is then supported by development of biological solutions like afforestation. Again, because no matter what your political leaning is, we all like trees. What is visible from the UK and US is increasing misalignment between technical maturity and deployment. High cost of development, coupled with fragmentation of removal activity across government agencies, sectors, and levels of governance, are preventing this alignment. The findings from this research created a framework for international collaboration that aims to align technical development and deployment to successfully expand the sector. This framework employs 3 strategies for international activity and 3 for national specialization to achieve a multidimensional sector. At the international level, there is a need to create a removals roadmap that develops off current annual reporting from the IPCC and includes creation of a robust carbon market. Organizing foundations for the sector now will guide the transition. There's also need for a coordination hub to align and inform regional strategies. And finally, there's a need to transform the constructs from which policy processes are created. Frequently, strategies remain linearly visioned, but the world is constantly adapting, and consequently, greenhouse gas removal's role is constantly changing. Policy needs to develop with us. It cannot be stagnant. It must be adaptive for sector success. At the national level, accurate and certified metrics must be created. There's too much uncertainty in greenhouse gas removal, owing to inconsistencies in reporting, which ultimately has led to exploitation and greenwashing. Metric consistency will prevent this. There is a need for national coordinating offices to verify and certify strategy, as well as support development of bottom-up approaches that closely align to localized social and cultural values, reducing inequity in future growth. And finally, there is a need for global education of what greenhouse gas removal is and why it's needed. Too often, it's seen as a climate solution to excuse high-emitting activities, but it's not offering a final solution for all climate action. Rather, it's offering a small but essential part of the equation. Implementing these strategies will work to achieve sector critical mass and ensure a just and safe transition. I will now hand over to Anna, who will continue to explore the options for national action to internally align the greenhouse gas removal sector.
Thank you. My project looked into the role of collective intelligence in creating a coherent and shared vision for the future of removals in the UK. Collective intelligence is the enhanced capacity created when individuals work together, and specifically when and how this enhanced capacity can become more than the sum of its contributing parts. It's a term for something that many of us are familiar with. For example, the crowdsourcing of COVID symptoms from millions of people at the beginning of the pandemic allowed us to understand the virus quickly. Or Wikipedia, the creation of the largest reference work in human history. And even today, by bringing these 10 presentations together, we're hoping to give you a deeper insight into what we believe is necessary for the future of energy policy. It's very likely that we will need greenhouse gas removal in order to keep to global temperature increases of below 1.5 degrees Celsius. However, many of these removal technologies remain at an early stage of development. The UK has invested over £1.5 billion in carbon capture and removal projects in order to meet the scaling challenge. These initiatives have been dispersed across a range of institutions, which allows for independent thought, development, and new perspectives. However, there is a risk that without a formal mechanism to incentivize collaboration, communication, and information sharing, that we may be pouring this capacity into a fragmented sector. This risks not only inefficient public spending and duplication of work, but also the isolation of capacity and the lock-in to certain technological paths. A series of workshops and interviews were held with stakeholders across government, academia, and the private sector in order to firstly understand the issues that they perceived for the future of the sector, as well as the potential for collective intelligence to alleviate some of these concerns. There was a perceived risk of stakeholder fatigue due to stakeholders being involved in a range of projects, each with different requirements, obligations, and schedules. Without proper and effective management, this could lead to lower levels of engagement. It's also essential for us to be able to deploy at scale, and without a certain level of societal acceptance, it will be difficult to achieve this. So it is essential that we understand public attitudes at both a general and technology-specific level. There were also more systemic concerns around the lack of awareness of ongoing work in the sector. It was found that these concerns tied into the need to build a shared understanding of the role of removals. Collective intelligence thrives on bringing together a range of people, ideas, and perspectives to create something greater. In removals, bringing together these different projects, the technologies and perspectives into one collective could mitigate the risk of fragmentation, whilst also creating a vision which is greater than the sum of its contributing parts. But how do we take the theoretical and make it operational? It is recommended that we establish an online platform which visualizes the system processes, dynamics, components, and goals of the ongoing research in the UK. This draws on thinking from collective intelligence assemblies, and in particular, the element of shared memory of what does and doesn't work, and this is particularly important to a rapidly growing sector. It would involve the compilation of information on the projects and the initiatives, how they relate to each other and how they interact, into a publicly accessible commons. Establishing this commons would allow us to create a more collective culture and increase transparency as we build a more robust UK greenhouse gas removal sector for the future. This presentation focused mostly on the decentralization aspect of collective intelligence, but democratization is also critical. Ariella will speak more to this now.
Thank you, Anna. As my colleagues have successfully demonstrated, in order to reach net zero, we must respond to a set of challenges. In my research, I focused mainly on two challenges. The first is our difficulty as humans to imagine and prioritize long-term futures. And the second is the difficulty to do so in a collective and inclusive way. The tendency to overlook long-term impact in favor of immediate gains is especially dangerous when facing climate change, a global challenge that, although is showing its effects now, is set in the long-term future. To overcome these challenges, my project recommends that instead of relying on a small group of academics, politicians, and consultants to determine the possible futures, by adopting participatory futures, we can introduce the process of systematically and inclusively preparing for a variety of sustainable futures. Participatory futures is the practice of collectively exploring the landscape of possible futures and can be located in the intersection of future studies and public engagement. Although initial steps to apply participatory futures into climate action have been taken, it remains a niche tool. An initial objective of this study is to provide guidelines of the ways in which participatory futures can be better integrated into institutional processes for net zero policy making. This research found that participatory futures has the potential to address the current gap between nationally declared climate targets and the actions taken to reach those targets, termed the action gap. At first, the components of the action gap were investigated and can be divided into three categories: the way we think and act, the way we communicate, and the way we govern. This typology is aligned with the emerging understanding that in order to reach net zero, 60% of emission reductions will demand societal and behavioral changes on some level. To better understand the challenges of integrating participatory futures, I looked at Climate Assembly UK as a case study for engaging citizens in decision-making around net zero. Climate Assembly UK was commissioned by Parliament and included 108 randomly selected citizens representing the UK. Over the course of 6 weekends, they learned, deliberated, and proposed recommendations on the way in which the UK should reach net zero. By taking a qualitative approach and conducting interviews, this research found that there are two major barriers for integrating outputs of participatory futures into climate policymaking. The first is the credibility and independence of the process, and the second is centralized, disengaging governance. As a result of a thematic analysis, two mechanisms are strongly recommended to enable the integration of participatory futures into climate policymaking. The first is this as establishing of an independent oversight body that will ensure that the design and the outputs of such processes are independent and credible. And the second is setting a national public engagement strategy that recognizes the need for a range of different engagement mechanisms to improve decision-making. This would ensure that Parliament and government have a system in place to integrate outputs from participatory processes. Although participatory futures can be applied to all levels of governance, decentralizing decision-making is essential for scaling up such processes. A specific example for decentralized governance and the importance of inclusivity will be presented by Julia, who looked at energy and governance for disadvantaged energy consumers.
Thank you, Ariella. I agree that engaging the public and understanding the social sphere in which we live are an essential part of delivering the energy transition. My research focused on analyzing the evidence available on how fuel poverty is experienced by disabled people in the private rented sector and the policies that relate to this vulnerable group. Disability, fuel poverty, and renting are three complex and interrelated areas of governance, and looking at the intersection of these vulnerabilities can give us an idea of the impact of national energy policies on a smaller scale, that of households. The framework of energy justice can support our understanding of the hardships facing the fuel poor by looking at the recognition of their needs, the procedural barriers faced when taking part in decision-making, and the unjust distribution of resources and of access to goods and services. Let's first take a step back to ask, how did I get to this topic? Well, the basis for my research is still grounded in the race for decarbonization. The UK housing stock is among the oldest and most inefficient in Europe, and the emissions from domestic heating make up 14% of the national amount. As the vast majority of currently existing buildings will still be in use by the time we're supposed to have net zero emissions, it's paramount to quickly decarbonize domestic heating and to make homes more efficient. At the same time, this urgency is an opportunity to effectively address one of the injustices which make our energy system unsustainable and anachronistic, the issue of fuel poverty, meaning the inability to adequately heat one's home. Unfortunately, many of the people that struggle in heating their homes live in the private rented sector, which makes up 40% of the UK housing stock and contains many of the lowest quality buildings in the country. A further piece of bad news is that many of these fuel-poor renters are also disabled. I systematically surveyed the studies which investigate this vulnerable subgroup to gain a meaningful picture of why this is the case and to make some evidence-based recommendations on how to improve the situation. There are three main issues facing this group emerging from the research relating to the three spheres of energy justice. On the recognition side, fuel poverty indicators fail to accurately identify fuel-poor households in non-urban areas, particularly coastal areas. In addition, the extra costs faced by families with disabled children and by older people are neglected by indicators. For procedural justice, renting takes agency away from the individual when trying to improve their quality of life or access to energy services and into the hands of landlords who have been shown to not always prioritize the well-being of their tenants, as I'm sure many London student renters will be aware of. Lack of affordable alternative housing and of social housing keeps disabled renters stuck. For distribution, the already significant portion of disabled people in relative income poverty face additional hardship in the private rented sector due to technical and financial difficulties in meeting disability-related energy needs and due to a lack of alternative housing. These difficulties are exacerbated for the elderly and for families with disabled children. Nevertheless, there are solutions to these issues, and they rely on addressing the shortcomings resulting from a national approach by providing local action. All recommendations rely on improving recognition, as this is the basis for designing effective policies. Firstly, localized identification of fuel-poor households is recommended, for example, by taking into account the socioeconomic profile of the community and the infrastructure available in the area. Secondly, it's necessary to raise awareness of the role that landlords, who are often disengaged energy citizens, can play in improving the quality of life of their tenants. Lastly, there needs to be more research to understand the energy needs of vulnerable users, and this could be done by involving the health and social care sector in local energy projects to ensure that households that could most benefit from local solutions are prioritized. So local action has been found to be a way of improving domestic energy policymaking, but how should an effective local energy system be set up? Well, Josephine has researched just this.
Thank you, Julia. As you've heard, local action will be fundamental to a successful energy transition. But UK energy governance in the UK faces major reform to reduce energy demand, accelerate change, and adapt to a decarbonised, decentralised energy system. Smart local energy systems can provide energy services and meet our fundamental energy needs whilst maximising local sufficiency and independence and improving energy resilience. But existing UK energy governance is highly centralised and will face specific challenges as focus moves to a local scale. My research looked into how these governance challenges can be addressed within an adaptable framework for effective system governance. Looking at some examples of local system governance challenges, it's immediately obvious that local authorities have a serious lack of capacity for energy activities and no legitimate role within UK energy governance. This must be addressed, as local authorities are uniquely positioned to understand local energy needs and interact with local stakeholders. This is further complicated by the transition from distribution network operators who distribute our electricity to distribution system operators with platforms for multi-directional energy flow. This is being triggered by new smart technologies and the role of the prosumer, where we as citizens can sell our own generation. Whilst it's clear some local system challenges are being addressed, there remains a lack of research on how governance can adapt to these new complex local energy systems, whilst ensuring security, carbon reduction, and meeting social goals. Through the evaluation of literature, pilot energy studies, and expert interviews, my research has found 8 effective governance principles, along with requirements and measurements that could be used to provide guidance on governance of smart local energy systems. This is split into governance inputs, i.e. what is required for effective governance, and outputs, which can be measured for continuous evaluation of system success. For example, the introduction of transparency and engagement can foster local trust and enable the design of systems tailored to local needs. So how could this look applied to energy system governance arrangements? Well, looking at the application of the framework to case studies, we see that the overarching principles can provide guidance regardless of energy system governance arrangement. Firstly, with Robinhood Energy and Bristol Energy, which are failed local authority-owned energy companies, retrospective application of the framework could have prevented up to 8 of the failings identified in governance reviews. This includes defining the functions within the governance structures, minimizing conflict of interest, and providing training. Looking at some existing energy system projects, such as Local Energy Oxfordshire, a DSO trial, the framework provides opportunities at a whole system level, followed by standardization across projects, contributing to future system learning. So we've looked at examples of current areas the framework could aid in governing local energy systems, but the outputs of my study recommend an effective governance whole system approach, where principles can be applied at the overarching system level for all stakeholders, including local authorities, network operators, and private sector actors. Then this could be carried through for standardization across individual projects, where requirements can be selected based on relevancy. If integrated within usual processes, this framework should enable integration at all levels and aid in the transition from pilot to permanent, facilitating governance that prioritizes outcomes such as security, rapid carbon reduction, and social goals. I will now pass on to Anna, who will conclude our presentation.
As presented earlier today, in low carbon technological development, creating the next generation of energy technologies is essential and highly important. However, the projects presented here look beyond the technical requirements. They assessed policy, market, and governance to set the strategy for a sustainable evolution of the future energy system. So, what is needed to develop the 4 megatrends that all these projects focus on? When it comes to decarbonization, ambitious and consistent policies that stakeholders can rely on will facilitate a successful transition to net zero, as well as alignment between different governance levels and stakeholders to reach common goals. To achieve decentralization, competencies need to be decentralized, and legitimacy, transparency, and accountability must be assured at all levels. This can be enabled by democratization of the system, as engagement on all levels is needed for an inclusive, equitable, and effective energy system. Finally, proactive and collaborative regulation ensures that high-tech digital solutions benefit us all and as well as the climate. As Antoine de Saint-Exupéry once said, "As for the future, your task is not to foresee it, but to enable it." And this future of MSC Sustainable Energy Futures is ready to do so. Thank you for your attention, and we welcome any questions.
Thank you for that compelling presentation. The next panel discussion will run until 3 p.m. BST and is led by Mervin Azeta. Again, remember to use the chat to post your questions, and I'll just hand right over to Mervin. Thank you.
Hello, good afternoon. Please confirm you can hear me. Very good. So this has been very interesting and insightful so far. I enjoyed listening to the presentations. I also particularly appreciate the diversity of thoughts that you all shared, as well as the focus on the 4 Ds of the energy transition. And we know that there's been a lot of conversations now, especially with the pandemic. There's so much uncertainty on the market, and a lot of the governments are prioritizing different policies. Their priorities are actually changing. But I do find, though, that most of the insights that you all shared were somewhat biased towards developed economies, and only little consideration was given to newly emerging economies. And we know that these economies are currently confronted with the energy sector transformations dictated by climate change mitigation agenda. And this presents a unique governance challenge for these economies. So I'm curious to hear some more nuanced thoughts on this. And also, as you know, the energy sector in most of these emerging economies are often state-led, vertically integrated monopoly driven by the needs of the national economy. So this leads me to my first question, and it's not directed to anyone in particular. I just want to hear your thoughts around what could be required to catalyze the transition to a decentralized system, as well as refocus governance in these emerging economies. So who's going to take that?
I'm happy to take this first.
Okay, great.
So my research specifically looked at the UK, but I think that there are some of the principles that I found that could be applicable to any economy, and specifically this idea of transparency and engagement and how important that is as we move to energy systems on the local scale. So I think it's about when we're having local energy systems, designing them with the needs of that specific local population in mind. And I think that this is more likely to encourage those citizens within those systems to be engaged in decarbonization because they can directly see the benefits and also understand what the changes are. So.
Great. Anyone else?
I'm happy to briefly add to what Josephine said. So again, to support the local aspect, when creating more sustainable systems of energy governance, I think it's important to make sure that other aspects such as, from my research, housing, welfare, jobs, and other areas of the human experience are included when designing energy policy, just to make sure that you don't then end up with inequalities that then create an energy imbalance later on.
Okay, thank you very much. Great response. Somebody else wants to go? Oh, we move on.
I can add a little bit to that. So part of my research looked into greenhouse gas removal technologies, and I think in that context, there's a lot of research which is being done on looking at community and local specific solutions, and instead of looking at a one-size-fits-all solution to a problem, it's looking more at, okay, what does this community need, and how might these effects, maybe it's environmental, maybe it's kind of the economic and social impacts, how do they look in that context? And part of that is kind of changing the regulation so that it highlights this regional specific aspect when applying for planning permissions or integrating demonstrators.
Okay, thank you very much to all three of you. So my next, you want to say something? Go ahead.
Sorry, yeah, if I may. Yeah, so my research focus on PPAs, but I think that when it comes to emerging economies, they can also be really helpful, as some countries cannot afford to have as strong subsidies as some first world countries have to boost the deployment of renewables. And so when they can have such strong subsidies, PPAs can work as a good backup to boost that deployment. So it's like a second alternative that they can use, while they can use also other subsidies.
Okay, cool. Thank you very much. So this morning, as I was reading the Guardian article, we suggested that every one of the world's leading economies, including all the countries that make up the G20, is failing to meet commitments made in the landmark Paris Agreement in order to stave off the climate catastrophe. And one of you mentioned that, the latest report from the IPCC is saying that, we're not even on track, and we're actually exacerbating things, right? Because we could very easily get to 3 degrees. But I'm wondering, these governments have made commitments. We know that they are having some really exciting ambitions to reduce emissions significantly by 2030 and to even reach net zero by 2050. But without near-term actions or local actions, like some of you had mentioned, achieving net zero is virtually impossible. So I'm here wondering what more could be done to stimulate the desired actions from all stakeholders, and not just businesses or private sector actors or governments, but from everyone to get us on track.
I can maybe start talking about that quickly. So digitalization can be a huge catalyst for behavioral change as well. And for digitalization to be more sustainable, we need more behavioral change in alignment with more digitalization. And one good example is maybe the COVID pandemic and the fact that we're all discussing this virtually again. I've also analyzed the potentials of telecommuting and virtual business travel. And there is some significant potentials we can unlock even in the short term. People got used to working remotely, and chances are high we'll have a hybrid format in many countries, even after the pandemic. And that's maybe a good example that behavior does have a great impact on overall mitigation, and also allows people to take part in this transition and to feel like they are part of it. And this also enhances more policy support, I believe. So digitalization can be part of the solution, not the complete solution, but help towards achieving this target.
And let me take you up on that just very quickly before we get some other responses on that question. So digital technologies will certainly be indispensable along this journey to a net zero energy future, right? They would help us improve safety, productivity, accessibility, and even the sustainability of our energy systems. But there are concerns about the evil of digital, like, cybersecurity concerns, privacy and data ownership and all that stuff, and even the consequent economic disruption that can come from any of this, right? So what could be done from a policy perspective or even a governance perspective to address this cross-cutting risk?
So I discussed this a bit in the topic equity of benefits, I'm calling that. So basically there's a risk with some innovations that these service providers are the ones who gather all the user data and will develop data monopolies, similar to what we've seen with other internet platforms. And in order to have a better transition in energy, a better transition than we have seen, for example, in social media, we might need more direct policy regulation. One potential solution would be an independent oversight of user data collection. We've seen some more initiatives in different parts of the world, for example, a GDPR regulation, which aims to make it more transparent. And maybe transparency is one important aspect that people also develop more trust in this. And then the second thing is ensuring that the benefits of data are not just accessible to the market leader, but ensuring that maybe even competitors can gain access. So independent oversight and transparency are key factors. And then the third question, will people be willing to share more data? I'd argue at the moment, maybe not. But we've seen they are willing to do so with, social media, other digital platforms. So as long as they can see the benefits of it, also the climate benefits, or the behavioral benefits of it, they might also be willing to share more. So these are maybe the three core components from this perspective.
Okay, great responses. Thank you very much. So let's get back to the first question. What more could we do to stimulate the desired actions from all other stakeholders? So like civil society, for example, you had mentioned the local communities. So how do we get them to act so that we can get back on track?
Thank you for the question. I can try to also answer it. So one of the findings for why we are not responding to climate change is because we're emotionally distant and disconnected from it. And what my research also suggests is that globally we should be emotionally connected to it. And one way to do so is to envision a variety of futures and also to use more immersive processes in order to see what it would be like to live in the world of 3 degrees Celsius rise or 5 degrees Celsius rise. And in that way, we're more emotionally connected. The need for change will be more urgent and we will probably act more urgently.
Okay, thank you very much. Ariella, that was good. Who else wants to try?
Yeah, I'll just quickly add on to what Ariella was just saying there. In being emotionally involved, you also have to be educated on it. So it's really just about increasing education, really localized, because the challenges that we face here in the UK aren't going to be the same for someone in a small community on the other side of the world. So it's really just about ensuring that the education is targeted to the individuals and really just increasing the portfolio that way.
Yeah, I think it's important that the education is contextualized and made sure that it's unique to the local population. Okay, great, thank you. So my next question is directed to, oh, you wanted to try, Alicia? I was coming to you, actually. I was coming to you.
Okay, yeah, I was just going to add on to what Victoria and Ariella said. Okay, and ultimately, whilst there is a massive focus on the kind of demand side response, I think it does ultimately translate back to we need adequate policy, and I think it does kind of stem back to the government, and that they need to create that policy environment that will kind of stir that direction of travel. So I think ultimately it just comes back to the government.
Yeah, the enabling environment is critical as well. Thank you. So let me just ask you the question I was going to ask. Okay. So from your research, I understood that businesses in the UK are considering internal carbon pricing, which I think is great. But I'm curious to know if businesses in other parts of Europe are doing the same. Otherwise, what are they doing today to achieve net zero emissions?
Sorry, you cut off a tiny bit at the end when you got to the thing about European countries or companies.
Okay, so let me repeat that. So I was curious to know if businesses in other parts of Europe are doing same today. Otherwise, what are they doing to achieve net zero emissions?
Yeah. Okay. So the Carbon Disclosure Project, they report information from across a lot of international companies, and there are a lot of European companies that are implementing internal carbon pricing. I think it isn't just a mechanism that is solely isolated to England or the United Kingdom. I think it is a mechanism that is being applied in North America and especially within the European Union. It's not something that is being considered within developing countries. But yeah, so within the European Union, I think it's kind of the same uptake that we are seeing in the UK. I think in the last few years, there has been a lot more of a increase and a lot more of an emergence of it being seen. And I think that can kind of resort back to some of my project involved having some interviews with net zero corporations. And so I had a really interesting conversation with someone from the financial services sector. And they did say that they operate within the European Union, like United Kingdom and European Union. And they did say that whilst it is or was seemingly a lot more relevant and fit for purpose a few years ago to kind of instigate behavioural change within companies, it may not be as necessary as it is now. I think there's a lot of kind of corporate mechanisms that are being thrown out there. I think there's a plethora of mechanisms available to companies, which makes it hard for them to see what is relevant to them, what isn't. But ultimately, I think it just stems down to, there is no one size fits all kind of mechanism for an organization. So whilst it is, you can separate it based on a kind of United Kingdom like market and policy environment, and then within the European Union, within that you're going to have so many different organizational structures. So I think the dynamics of internal carbon pricing will really play into that.
Okay, anyone wants to add to that?
Yes, I can add something about like the sourcing of greener electricity. Everywhere across Europe, there's like an increasing interest from companies to procure energy from renewables, and there's like this interest in engaging into PPAs that Anna talked about, to have like direct agreements with renewable projects. So we had in Nordic countries big companies like Google, Amazon, or Facebook that entered into PPA agreements or showed interest into going into PPA agreements, and the same in Spain as well. It's like big companies interested in sourcing electricity from solar projects mainly.
Okay, thank you.
If I can just add something.
Yes, please go ahead.
As Paul mentioned, there are big companies that are engaging in this type of contracts in PPAs, but there's starting to be a trend, and it has started in the Nordic countries, for example, of having contracts of smaller capacity, for example, like 1 megawatt, 2 megawatt capacity contracts. And so that allows for smaller stakeholders to engage in those contracts and to allow the deployment of new renewables. So that is also gonna help, and you're not gonna have to be this huge enterprise anymore to engage in this type of contracts. So that's also gonna be really helpful.
Okay, thank you, Anna. So I've seen a few questions come through, and I'm going to just go to them now. And so the first question is for Daniel, and it says, how probable is it that these 6 digital innovations will be implemented in the near term to reach net zero in the EU?
There's an old saying that it goes, it's difficult to make predictions, especially about the future. So yeah, it's hard for me to predict, but maybe a few points I can make about that. So first, the study explored best case potentials, and we asked experts about the fusion pathways. And the median expert opinion is that we can achieve the potentials I highlighted from a political, economic, social, cultural, and technical perspective. So there is some contribution towards net zero, so maybe 10–15% of the emissions gap we can achieve. How probable do I personally believe it is? I'd say in the current context of ambition, both in industry and in policy, even in the EU, probably not that probably we will achieve the potentials I highlighted. One example is even the industry, even automotive industry, for example, they seem to be more preoccupied with electrification at the moment. So those more long-term digital innovations aren't that interesting, even from a business perspective at this point in time, because there are more immediate things we need to do in terms of decarbonization. But there are great synergies from digitalization. Also in terms of policy, digitalization is a key policy objective from the European Commission. They even have a digital compass, which is being released right now. So basically, the value of synergy might be something that can leverage it. So personally, I'd say at the current state, not that likely, but I'd be optimistic, and I think there are good reasons to be optimistic that we can unlock potentials even by 2030, and then especially by 2050.
Optimism is great. Best to be there. Okay, so the next question talks about data and digitalization and how they play a crucial role in decarbonization. But they're wondering if the panel could comment on how policy, markets, and governance should be developed to incentivize data sharing.
I guess I could just quickly start this one off. So my project was not focused on digitalization at all, but I think there are some findings that I could kind of extrapolate that could relate to the theme of data sharing. I think it would be vital to kind of instigate more transparency again within policymakers. I think that would definitely help to incentivize it. So yeah, so just greater transparency.
Okay, anyone else?
Yes, I can also add something to it. From my point of view, if a community is willing to share data, maybe in return they can get some advisory or consultancy to better minimize their emissions, and in that way both sides can gain from this.
Okay, great.
I'm happy to add to that as well. Based on my research, I think in terms of increasing digitalization and data sharing, there needs to be an accountability towards fairness and accessibility of the way the data is, well, the whole life cycles of the data, how the data is collected, stored, and used later on. So particularly for users that maybe have different adaptation needs, some of my research has shown that smart meters are not always accessible, for example, for people that have vision impairments or other needs like that. So I think there needs to be a conscious involvement of designing the data collection and the data sharing for a range of individuals and not just the average user.
Okay, great stuff. Anyone else? Or we move on? Okay, so we take the next question. Are there any private PPA contracts permitted in UK? As this plays a major role and possible to affect the government power development plan?
Yeah,
so I'll take that again. Okay,
yeah.
cool.
Yeah.
If it's understood, yeah, go ahead.
Yeah, so there are private PPAs now in the UK. Most of them are physical PPAs, which are the ones that I focused on in my research. But there's also this trend of virtual PPAs, where there's no physical energy delivery from the generator to the buyer. There's this trend of virtual PPAs also increasing, especially as the contract for difference, this type of subsidy. These are virtual PPAs. So these are increasing. However, the subsidies are limited. There's only a certain amount of projects that can actually access them. And for those, PPAs are a great alternative. So it is expected that the government power development plan it's gonna improve. It's gonna increase. It's gonna change for the best. And PPAs are gonna play a very important role. The government has said that the subsidies are gonna go on for like at least 5 more years. But at the same time, during those 5 years, there's expected to be a big increase of PPAs. So it is expected to be affected, but positively.
Okay, great. Anyone else? Okay, so we take the next question. So very interesting projects, or really interesting projects, the person has said. To the panel, how do you see policy and governance changing to incorporate a net zero agenda?
Yeah, I'd love to. I'll
Victoria, go ahead.
So I think what we're going to start to see in government, the change we're going to start to see is it's going to respond more to how society is acting. You know, we're seeing lots of real activism coming within the net zero agenda, within the movement, and a lot of movements coming from the bottom, from individuals. And I think the government's going to start to respond, and it's going to, you know, adapt to what society wants, and that's really how you know, the change is going to be seen. And with that, through my research, a recommendation that I came to near the end of it was that policy processes will just have to be adaptive and really resilient to the changes in the environment. And that is social, that is what the individuals are doing, but it's also environmental and cultural and economic. So whatever changes are happening in society, policy's going to adapt with it and needs to adapt with it. And that's something that we're going to start seeing.
Great. Jasmine?
Yeah, so kind of going on from what Victoria said, I think we can go back to the 4 mega trends that we suggest in our presentation for the net zero agenda. So democratization, digitalization, decentralization, and decarbonization. And I think that it's really about how policy and governance can adapt to these mega trends. So, for example, looking at, you know, my research, which focuses on decentralization, as an example, there's something in the UK called local area energy planning, which is run by Ofgem and Energy Systems Catapult, which is looking at the optimal technology mix for local energy systems. But there really isn't a lot that says how policy and governance can really help things like this be implemented. So it's really looking at how governance focuses on the local scale, whether that's, you know, increasing capacity and roles for local authorities or focusing on community engagement. And I think that those would be really, really important.
Okay, thank you. We'll take 2 more questions and probably wrap it up. So for Ariella, thanks for your presentation, really interesting. BEIS are currently drawing up a public engagement strategy. What key features would you like to see in this to enable the inclusion of participatory futures in reaching net zero?
Thank you for the good question. So I would hope to see 3 major things that would answer 3 barriers that I found. The first thing would be to develop some sort of committee or body that would be in charge to respond to public engagement processes, because currently, even if we have public engagement processes such as Climate Assembly UK, it takes such a long time to get a response. Sometimes even there is no response, and that can really demoralize the participants. So this is crucial to communicate properly and to cooperate. Secondly, and very important, I would hope to see decentralization of power competencies, because currently on the local level, there's a statistics that says that only 3% of direct emissions is in the power of local areas. And in order for local change to happen, we need to change that. We need to see that if a community wants to make a change, it has the power to drive to that change. And this is very important. And thirdly, I would very hope to see, as I said, more immersive ways of involving the public, because yes, that will allow emotional connection and it allow more imagination in how we tackle this. So these are the three main things I would hope to see in the new strategy.
Okay, thank you so much. My next question will be to every one of you, anyone who can answer. And someone is saying, from their point of view, government should enforce net zero policy to every individual industrial organization and promote free trade carbon market, as these will be important tools to achieve net zero target globally. However, the person is curious about your team idea. What is the most important strategy or tools to achieve 2050 net zero target?
I'd like to start with that one. I think for me, it's more of a mindset change. I think starting to think systems. One of the things I've definitely learned throughout this course is you can't just look at one thing in isolation and greenify that. So if we look just at the generation source for electricity and we don't think about, for example, the rest of the system and the storage and the weather and all of that, that doesn't play in together. If I think about removals, if I don't think about the land changes in the food industry, then I'm creating more problems. And so I think we need further connectivity and appreciation for these interdependencies and interlinkages between all of these issues. And that's a really big challenge, but I think it's also a great opportunity that we have a chance to address so many things and think about sustainability beyond just carbon emissions.
Absolutely. Thank you for that. Anyone else? Okay, so yeah, go ahead, Victoria.
Well, I was just going to support Anna on that one and just say, you know, from the three presentations we've seen today, we clearly have so many tools available to us. And, you know, I think that's a great question from the audience, but it's not about one solution. It's about a portfolio. You know, we have all these tools, we have all these technologies, we have so many different governments. It's about really developing a portfolio of approaches and just ensuring that the externalities that do appear, that they're dealt with appropriately and that everyone can transition into this future that we are creating really justly and equitably. And yeah, that's what I'd like to end with.
Thank you. In 1 minute, I would like to take this last question. I said two, but I think this question is very important. If you had the power to implement one governance change today, what would it be?
I can start that. For me, looking specifically at the UK, it's how we move from pilot to permanent. So at the moment, we have a lot of really innovative and great ideas, great technologies, but they're really in these sort of bounded project stages. And I think the key governance change is how we move from those bounded projects to permanent system change, where, you know, we have these technologies integrated in our everyday lives.
Okay, thank you very much. So we've had a robust conversation, and I think that one thing is clear. We need reforms in the energy markets. We need reforms in policy incentives and regulations to help us advance the transition. But more importantly, scale innovation and attract investments to fundamentally transform the entire energy system, and not just across the spectrum of electricity, but heat, transport, and industry. And although the challenge is huge, and there are different pathways, we just must do what we have to do, and we must do well to put the 4 Ds, not just decarbonization, at the center of the decision-making across the whole system. And in today's rapidly evolving marketplace environment, we must engage a broader base of stakeholders. It can't just be governments and private sector actors doing the work. We need to engage local communities. We need to engage the civil society. We need to leverage collective intelligence, like I saw in some of the presentations. We need to take bold, strategic, urgent actions to lower emissions and advance the transition. So thank you very much for your presentations. They were fantastic, and I wish you all the best.
Stimulating discussions. Thank you to the team. And Mervin, thank you so much for the energy you brought to the discussion and your leadership. It was amazing. Next up, I am beyond ecstatic to welcome our keynote speaker, Damilola Ogunbiyi. I believe a lot of you might already know who she is and all her awesomeness, but kindly indulge me as I introduce this power woman. Damilola Ogunbiyi is the CEO of Sustainable Energy for All, Special Representative of the UN Secretary General for Sustainable Energy for All, and co-chair of UN Energy. She's also a commissioner for the Global Commission to End Energy Poverty and the co-chair of the COP26 Energy Transition Council. She is a global leader and an advocate for the achievement of Sustainable Development Goal 7, SDG 7, which calls for access to reliable, affordable, sustainable, and modern energy for all by 2030, and in line with the Paris Agreement on climate change. Kindly join me to welcome Damilola. Thank you for joining us.
Sorry, I'm just trying to deal with technology here. Thank you so much for having me. Can I go straight into my presentation?
Yes, please go for it.
Okay, great. So I think I've been allowed to share. Okay. All right, so thank you so much for having me here. I'm going to try and be of high energy on like 4 cups of coffee because we started very early with Asia this morning, but really, really happy to be talking to young people, to be youth, because I really feel that you are the future. I was very, very lucky to head an organization at the age of 27 in the largest city in Africa, in Lagos, where I was the general manager of Lagos State Electricity Board. A few years later, I was asked to be the senior special assistant to the president of Nigeria, focused on the power sector, and then also working with the vice president. And then finally, before this role, I worked as the first female managing director for the Rural Electrification Agency, where that was basically the focus and the passion of my life, which is giving people who don't have any access to electricity access. It was really interesting hearing the discussions we were talking about previously, talking about, you know, the power systems and grid and not grid and carbon or not carbon and all these different things. And that's great when you have a choice, but when there's almost 1 billion people that have no choices in that, it's really important to develop programs and clean energy programs that includes women and youth first and foremost, but really, really leaves no one behind. So I'm going to start with, you know, what is Sustainable Energy for All and what's SDG 7? So Sustainable for All is basically the only organization mandated by the UN to really kick in gear SDG 7. And SDG 7 is access to affordable, reliable, sustainable energy and modern energy, because people forget the modern part, for all by 2030. And this should all be done with the Paris Agreement on climate change. This is the decade of action, if people don't know. And, you know, we think about 3 pillars: data-driven decision-making, which you should all be familiar with, being part of a university, partnerships with high-impact countries, and implementation on ground. There are 3 main targets. Universal access is split actually into 2, access to electricity and access to clean cooking. And then we have access, obviously, in increasing our share of renewable energy and then doubling the rate of energy efficiency as well. So what is the challenge right now? I think it's really important to look at just the situation. These figures are for 2019. There's always a backlog of about a couple of years. And what it shows is that 759 million people have no access to electricity. But what is even worse is if we continue at this pace of business as usual, 760 million people will not have access even at 2030. It also shows that 2.5 billion people don't have access to electricity, which is about a third of clean cooking, which is about a third of the world's population. We're increasing the renewable share, but that's mostly in the developed countries and some emerging economies. we could do better. And on doubling the rate of energy efficiency, if we continue, we will not hit that 3%. And I want to break it down to absolutes here. And what it shows you is my continent, Africa, is responsible for almost 80% of people that don't have electricity. And if you look at it in terms of a waterfall, my country, Nigeria, is responsible for about 90 million people not having electricity, which puts it at #1. It used to be India, but India has done massive thrives in terms of electricity access. It doesn't mean that countries are not providing access, but what it does mean is that population is outpacing a lot of electrification. But what is also important when we talk about energy access, and being a Black African woman myself, is just the inequalities in terms of energy consumption. So, you know, just being born Black African like I was, we are already almost 20 times as a disadvantage of the average American person because of the small amounts of energy we have at our disposal. And these are the people with energy, not even the people without. So in terms of sub-Saharan Africa, if you take away South Africa, you're only dealing with 81 gigawatts, which is roughly about what happens in countries like Germany. And this is exactly what this slide shows. It is really unacceptable if we're talking about just and equitable and, you know, the just transition and bringing everybody along and being truly inclusive, to have sub-Saharan Africa with 1 billion people only having 81 gigawatts, because we see the direct correlation between energy availability and economic growth. So in terms of clean cooking, which is a place that's very overlooked in many cases, you find that the Asian market actually has a lot more people without access compared to the African market, but it's still quite bleak overall. And right now, in a time that we're living, it's really unacceptable that, at least in Africa, you know, this is a cause for a lot more gender-based violence. Think about 1.6 million African women die from the fact they're using dirty fuels. And it's actually one of the highest causes of climate change and land use change, because people are cutting down trees at an alarming amount. When you look at this, China and India are the top countries in terms of the access compared to their populations, and then you have Nigeria as well. So just wanted to give you like actual data on what exactly is going on. So what it also means in terms of clean cooking is, you know, just the fact that, you know, women have to walk 5 hours a day. It does take away from, especially women and some children, living undignified lives. It causes up to 4 million people to die prematurely every year, and it's just a really bad emitter. So we have to find something to deal with clean cooking, and most of it lies in the fact that it's just not attractive enough. People just don't talk about it enough, and they don't understand the risk it has with climate, because it, for some reason, hasn't been linked to what is a just transition. But what we should know, and what should be very, very clear to everybody, is that we cannot say we're going to achieve our climate targets by 2050 if we don't achieve SDG 7. So I wanted to just quickly show you, what's happening in renewables. As you can see, a lot of this is happening in North America, Europe. It's not really happening in Africa and the global south. And just so you saw the data of what is happening in terms of the energy intensity. And I believe this presentation will be shared with all of you, and I can come back to any of these parts. So one of my goals, and one of the reasons why I exist and I'm in this role, is to really emphasize the global energy transition must be inclusive, equitable, and just. So it shouldn't be about any one country dictating to another country what they should do, and it shouldn't be about hypocrisy. We need, in terms of just energy access on its own, not even about energy transition, globally about $41 billion, and we don't have 41 billion going into that. When you put into account just the amount of money the global north has spent on the pandemic, the COVID pandemic, something about $17 trillion have been spent. So when people say there's no money, that actually gets me a bit annoyed, because I'm like, when there has to be money for a big pandemic, the money seems to appear somehow. It's also important for you to understand the equitable amount. So when people say no funding, limit funding to all these things, just what the sub-Saharan African region is responsible for. And it's responsible for only, less than 1% of global emissions right now. But it is the beneficiary, unfortunately, of a lot of climate issues. So there needs to be the equitability involved. And then when we talk about just transition as well, we have to also think about what does happen to clean cooking. Is it okay for countries to be able to determine their just transition and other countries not being able to do that? So one of the ways to counter all the doom and gloom I've spoken about is to showcase that clean energy and the clean energy offer is the best way to go. We already know that every 1,000 connections to decentralized energy solutions creates 25 jobs, 25% of food and waste isn't lost because of the cold chains for agriculture. You know, even the amount of people going to hospitals increase when they know there's electrification by like 69%. And this is particularly important with the vaccine. The vaccine is currently not equitable the way it's distributed, but what people don't report is the amount of vaccines that are wasted because there's not enough electrification in the health centers in a lot of these developing countries. And 59% increase in wages for women when they work in energy access, which finally puts on par with their male counterpart. And that is very, very important. I'm going to go into what does transition mean for a developing country? You know, everybody say, make your net zero pledges, and that's fine, but it's still a pledge, right? What does it mean? What do you have to do? And we showcased Nigeria because Nigeria isn't only about a consumer of oil and gas, but a lot of the GDP comes from that. So when you're telling countries to transition out of it, you have to think about economically what happens to them. And one of the key things is you need to alleviate people out of poverty. So when you hear some countries saying, oh, this is what's happening to my manufacturing sector, my transportation sector, and my hydrocarbon sector, it's great if you have it, but if you don't have it and you want to get there, what are the different ways you could do it? And what is shown in the case of Nigeria is that to get to net zero by 2050, apart from everything that has to happen, in the transport sector, agriculture sector, building sector, power sector, industrialization sector, it is the electrification of an entire economy, and it will cost at least 400 billion above business as usual spending. So where's this money going to come from? It also means that a country like Nigeria would, and if it's going the solar route, because I think that's the most attractive from our analysis, will have to be installing something of the regions about 7.1 gigawatts of solar energy every single year. That is an important point because that is more than the grid actually in Nigeria produces every day. So this so we really need to guide developing countries, and we just can't keep on shying away from, oh, they don't have the policies or they don't have this. Where is the funding going to come from? And one of my key takeaways is making sure that this is represented at the highest level and these countries aren't left further behind. So now brings me on to the role of youth in achieving SDG 7. I honestly believe this is the best time in history for youth. We're having kind of two major events this year. For the first time in 40 years, many of our lifetimes, there's a conversation about energy. I'm really excited the conversation is happening, but it's quite sad that it's taken 40 years since energy plays such a key role in climate. It's scheduled between the 22nd and 24th December, which is next week. I hope a lot of you people join. We do have some youth that will be speaking, so that's great. And one of the key outcomes of what we're trying to develop are energy compacts with youth. Things like Student Energy have already put in the energy compacts, which is what are the actions you're going to take in line with Paris to achieve SDG 7 by 2030. There's also obviously the COP, and then aligning what the energy transition pathways will be to the clean energy offer is also key. It's not a coal or a not coal conversation like everyone thinks. That's a simple part. It's how do people transition and how do they transition cleaner, taking consideration just some very, very key factors like the labor forces, their just transition and their own economic growth. And it's really important that the advocacy and the leadership that influences global policy to support a just and equitable transition is uplifted. We need to get this agenda of have people having basic energy, people being able to watch us today because they have some form of electrification up there, just like how we have climate and movements around that. So this is just the roadmap of exactly what we want to do, what's happening. Very key for us to have a 2025 milestone because we only have 9 years to go. And then after 2030, start working towards 2050. So it's just to show you that we do have a global action plan and the high level dialogue happening next year. It's the beginning, not the end of a process. Also in terms of, advocating and innovating, there's a lot of really amazing energy entrepreneurs, getting them, a little bit up there. A lot of people tweet about climate activists. They don't really tweet about energy activists and energy entrepreneurs and just the amazing stuff they are actually doing on the continent is also really key. Make your voice heard is always important. A bit that might not be in here, but it should be in there, is become a policymaker. I think my role was instrumental when I joined government, and being able to join government so young, I could shape and innovate some of the discussions. So not always staying at the sidelines, for me is very, very key. And I'm also proud to say, in terms of my organization, Sustainable Energy for All, we have about 41% of our staff under 35. Also join global networks. We work with lots and lots of global leaders. We had our first youth dedicated session, which was the key goal was that anybody who organized it had to be under 30 in the organization. So that was really cool. Please join us, participate in our events, or develop your own event and ask us to participate. You really need to amplify the voices out there from the global north and the global south, and people just understanding how privileged they are to have electricity, to be speaking on a computer, to have an iPad, to have an iPhone, and start thinking of how you use energy. How much energy does that app actually download? Do you have to have your laptop on 24 hours? Can you switch things off? It's really important for us to be conscious as individuals. So we can all contribute to making a difference for people and planet. And we can all be leaders in sustainable development today. So we have a hashtag Youth Lead SDG 7. And I really, really look forward to all of you participating in our journey. And if you have any questions from me, I'll be happy to take it. Thank you very much.
Thank you so much, Damilola. That was amazing. I don't even think I have the words. I'm not sure if there are any questions, but let me just check that. No, I don't believe there's no questions have come through. But if there are any, I would gladly send that through to you and figure out ways to communicate the responses.
Okay, fantastic. Thank you for having me again. And, really looking forward to you guys joining in next week and sharing just your thoughts with us on how we can fulfill our mission.
Definitely. Thank you again.
Bye-bye.
Bye. So I'll hand over directly to Faye, Dr. Faye, who's going to just give us our closing remarks.
Okay. All right. Thanks, everyone. Really quite enlightening presentations. A lot of for me also to digest. But one thing I can say is I'm more confident that we will get our decarbonization as we wanted from what you have mentioned. So yeah, it is quite challenging year, I would say, for us, but particular for you, our students. But I mean, from what I can see from all the presentations, I can see that's how kind of excellently you have finished the kind of the whole course. By now, we are approaching to the very end. So as the director of this course. I'm really proud and privileged to work with all of you together. I think one of the core, elements in our course is working together. Particularly, we have all these coursework activities all together. That's really be challenged by kind of these remote activities and limitations. However, from the older presentations, I can see that you all study together, work together, and play together. I think from I would expect you to get from the course is not only the knowledge, but also you come join that course alone. But when you leave, you will go with all the friends together. So yeah, before the close of the session, I think it's quite important to send some regards to all the organizers and participants. Really glad to see so many our audience, particularly our keynote speaker, gave really excellent view about what we have mentioned already a lot of times in our course. Energy is not hard. When it comes with so many conflicting objects, it is the part that really challenges us, right? And also we have to, I would like to send my regards to all the hosts, the panel hosts. I think all the discussions are really excellent. I think your students all challenged and also shared your really pushed out share your idea, your visions with all the audience. That's excellent. And also, of course, we have to thank all our student organizers, Avik and Adia. They really spent quite a lot of time to support organizing the event. That's really appreciated. I don't think it can happen without them. Definitely, we have to thank Mark and Paul. I'm not sure if they're there for their supporting our training. Last but not least, our staff members, Connor and Gavin, really spent a lot of energy, effort, so that we can really run smoothly of the whole session for today. Right, before I will save something for tomorrow. So the last thing I would like to say is stay tuned for the students and audience. We will resume our session tomorrow, same time, 12 p.m. I will hope to see you all there. And also we will have the dinner together with some of you who are still in London. I really look forward to that. I think that will conclude today's session. I will see you all tomorrow. Thank you very much.